Welcome to the IROS workshop on bringing geometry methods to robot learning, optimization, and control. Robots are required to react to new situations, act in unstructured environments, and overcome uncertainty, which involves outstanding adaptation capabilities that rely on a harmonic interplay among planning, control, and learning. For success, a key ingredient is to empower algorithms by considering geometry-aware formulations. Geometry is paramount to design robust, stable, and data-efficient methods in robotics. This is the topic of this workshop, and we are excited to have experts in different fields to discuss the importance of geometry in robotics, such as Luca Carlone.
I'm the director of the Spark Lab at MIT, and the Spark Lab works in the broad area of robotics and autonomous systems, but in particular we care about perception and computer vision for robotics.
Joan Sola.
My name is Joan Sola. I am a researcher at the Robotics Institute in Barcelona, mostly doing state estimation for mobile robotics.
Taeyoon Lee.
You can see that the natural gradient-based adaptive control, as shown in the very right side of the video, quickly adapts and converges toward the reference motion.
Bruno Adorno.
In these experiments, both robots communicate with each other, but just one of them has the information about the human hand pose. As a result, deformation is always a function of the human hand pose.
Subrayit Bhattacharya.
This just shows that the simple complex search, the S star search, finds paths that are much closer, but that are much closer both in terms of cost or length.
Maxim Ligachev.
Driving along the shortest path, then you get a difference between 264 seconds planning versus 62 seconds. If you just use a heuristic like a Euclidean distance heuristic, then forget it, that's just not going to be solving it at all.
Anastasia Varava.
So this is a shirt that is unfolded, this is a shirt that is completely folded. We're going to construct a latent space representation of the state space of the objects.
Mustafa Mukadam.
My name is Mustafa Mukadam, and I'm a researcher at Facebook AI Research. Today I'm going to talk about how to design and learn reactive motion policies and get robots to move and do things like you see on this slide.
Luigi Malago.
The damped KL Lagrangian and damped KL Hamiltonian, which are basically equivalent dynamics, which however are associated to different speed.
This workshop is organized by Noémie Jacquier from KIT, Leonel Rosso from the Bosch Center for AI, Soren Hauberg from DTU, Hans-Peter Schröcker from the Universität of Innsbruck, and Suvrit Shah from MIT. We are fortunate to be sponsored by the Bosch Center for AI. To watch the invited talks and spotlights of the accepted papers and interact with the speakers, please visit our website.
Welcome, everyone. First of all, thank you very much for being here, to all of you. To start, just let me thank the co-organizers of this workshop. They have done a pretty nice job. And let me tell you that the organization hasn't been easy due to the current situation. But believe me when I tell you that we did our best to have this wonderful workshop and to try to gather all the people that are interested in bringing geometry methods to different kind of fields in robotics. And we are really excited about this. So just let me also apologize due to the wrong time zone that we had in our website. The winter change time somehow messed it up, but I think that we should be all fine. So as you already know, the talks of the invited speakers are both in the IROS platform. So you can also watch them there in case you haven't yet, or you can also visit our YouTube playlist that will be always available. There is something super cool that I would like to share with you, and is that in our YouTube playlist, we have, I think that more than 1,000 views already. Also, of course, also covering the trailer of this workshop. But I think that's a really, really nice number for considering the timeline that we have currently with the starting date of IROS. So that's super cool for all of us. We also got quite a few questions for the speakers using the Google form that we set in our website. You will know a little bit about this later on. So now let me tell you a little bit about the agenda for today. So we'll have 3 exciting hours ahead of us, starting with the first Q&A session, where actually Luca Carlone, Joan Sola, and Bruno, and Taeyoon Lee will be answering some of the questions that we got in our webpage, but also some of the questions that the audience may have. So please feel free to ask and to bring up any questions that you may have. After that, we're going to have the first poster session with around 7 posters that will be presented using the spotlights presentations. And we'll have also a Q&A session for these papers. Later on, we'll have a well-deserved coffee break of 15 minutes, so you can go and take some coffee, some tea, or also you might take the chance to talk with some of the attendees here in the Zoom chat channel. After that, we'll basically proceed in a very similar way. So we'll have a second Q&A sessions for questions for Subrayet, Maxim, Anastasia, Mustafa, and Luigi. And then second poster session, followed by a panel discussion where we're going to bring up some interesting questions to some of our speakers. And finally, we'll close our workshop with the announcement of the best paper of the workshop, which is, as you may know, sponsored by the Bosch Center for AI. So let's start with the first Q&A session then. So I think that Noemi, is your turn to take over.
Yes, so let me just activate the camera. Okay. So we're going to start the first Q&A session. So with the talk of Luigi Malago, of Luca Carlone. So maybe I will start with one of the questions that we had in our Google form, and after that, yeah, feel free to ask questions if you have some. So Luca, are you here? Yes.
I am. Hi everyone.
Perfect.
Good morning / good afternoon / good night. I don't know.
Okay, thanks. Perfect. So the first question that was asked by Federico on our Google form is, during the presentation, you did not explain the process of classifications of inliers and outliers. And I wonder if this is critical for the algorithm. If so, how does this classification is done?
It's a great question. The classification is something that happens naturally out of the optimization. So it's not a separate process. You solve an optimization problem. So let me give a little bit more context maybe. In the presentation, I was talking about algorithms for robust estimation with outliers. And we have a novel technique essentially to solve the corresponding optimization problem globally, despite the fact that they are NPR, they are like, non-convex and so on. And the trick was to formulate these optimization problems by essentially including the variables that you want to estimate typically in perception, you estimate poses of objects, you estimate trajectories of the robot and so on, but also include binary variables in charge of deciding whether a measurement is an inlier or is an outlier, is a good measurement or is a bad measurement. And the way this works is that the variable and these binary variables are linked together in a sense that the binary variables are forced to classify a measurement as an outlier if the corresponding error is too large. So what happens in practice is that you set a threshold saying measurements with error larger than this epsilon or this threshold that I set must be outliers, and measurements with small error are inliers. And by solving the optimization problem, that classification happens naturally. You just have to specify a threshold that you want for the inliers. And again, just to mention a few more details here, these optimization problems we solve are extremely tough. What we do is to resort to convex relaxations, and in particular to semi-definite relaxations. And we use tools from polynomial optimization essentially to do that. The result is that we get, for the first time, we're able to get in polynomial time global estimates for these robust estimation problems, and the convex relaxation are smart enough to tell us whether they were able to solve the estimation problem to optimality, or they will tell I was not able to solve it in the worst case. I hope this is answering, otherwise I invite also the attendee asking the question to follow up. I'm happy to clarify more. And maybe what I can do is also to share screen real quick to show what I was talking about, if you guys want. Or do we want to move on with the next question, Noemi?
So I think Federico, who asked the question, is online. So if Federico, you want to say if that answered your question, you can take over.
Maybe in the meanwhile, while Federico is unmuting and so on, let me share screen.
Yeah, sure.
And let me, I don't know if you can allow that, Noemi. I cannot right now.
I'm trying, so I will stop sharing and you can take over.
Thanks, okay. So right now it's telling me that I'm not allowed, but let's see.
Now you should be allowed.
Okay, thank you. Okay, so let me see what's a good slide for this. So I think the easy way to understand this is that we're moving from quadratic costs, least square costs, to robust estimators in which the cost becomes flat for measurements with large error. And an easy way to understand, the role or the way these binary variables or this classification happens is just to understand that the binary variables are controlling the transition between the flat behavior, the flat portion of this cost function in which, you essentially want to mitigate the impact of an outlier, and the quadratic behavior, which is where you have inliers, right? So that's the only role of the binary variables. They are just encoding this cost function.
Okay, thank you very much.
Yep.
It was a nice answer. So maybe I will share again my screen, or maybe you can keep it actually. So does somebody in the audience have some question for Luca? If yes, feel free just to unmute and ask your question. Okay, so if not,
I also would like to thank you guys for organizing these. I've been watching a number of videos, from the other speakers and so on. I think it's a great event. So thanks for putting this together, and thanks for inviting us.
Thank you very much. That's a very nice feedback to have. Yeah, thanks. That was also a great event for us. So thank you very much. So maybe I will ask you another question of our Google Doc. So in the teaser plus algorithm, you reformulate the robust 3D registration in a QCQP algorithm. How is the constraint that a variable is a rotation matrix so that it belongs to SO3? In the robust 3D registration is translated to Euclidean constraint in the QCQP.
So the question about the QC, can you repeat the last part of the question?
Sure. So how is the constraint that a variable is a rotation matrix in the 3D registration is translated to Euclidean constraints in the QCQP?
Yeah, it's a great question. So just for the audience, just to visualize what we are talking about, like, we have problems like that in which we are essentially solving a 3D registration problem in which you want to match two-point clouds. And this is a very, very general problem in computer vision, and is about doing object detection in point clouds, or is about doing scan matching in robotics. So it's a very general model. And just to recap the formulation here, you can see on the top left that the equation is about doing this trick of estimating a variable x through nonlinear optimization and having these binary variables theta, which are in charge of classifying inliers and outliers. And for the registration, what happens is that the expression of the optimization problem is the one at the bottom, in which for example, we try to look for a rotation R, which is aligning the 2-point clouds A and B. And I think the question is about more than the cost function, which is, for those of you working on this, is already pretty clear, should be about the constraints. So R is in SO3, and SO3 is the group of 3D rotations. And what happens is that you can express the group of 3D rotations as a set of quadratic constraints. The intuition there is that the definition of the group of SO3 is the set of orthogonal matrices, so matrices such that R transpose R is equal to the identity, with determinant +1. And R transpose R equal to the identity is pretty clear, that is a quadratic constraint, quadratic equality constraint. And you can also manipulate the determinant constraint to make it quadratic, because the determinant constraint is just enforcing that the rotation is describing a right-handed reference frame. So it's something that you can enforce in terms of the cross products of the columns of the rotation matrix. So in other words, you can just write these as a set, described by quadratic constraints, and that's exactly the type of constraints that you can relax in a QC/QP. I would say that probably the easiest way to understand these, just if you guys are less familiar with the 3D setup, an easy way to understand the type of relaxation we do is to think about 2D rotations instead of 3D rotations. A 2D rotation can be described as an angle, but can also be described as sine and cosine of that angle. And in that case, in 2D, the constraint would be that the square of the sine plus the square of the cosine is equal to +1. So you end up with a quadratic constraint. It's very easy to see in the 2D setup, but the same is also true in 3D. And that's exactly what we do. So we have a set of quadratic constraints, in this case, describing something about the rotation set. And we have to do in the teaser++ paper a lot of manipulation to show that actually this theta, this variable's theta, you can manipulate the cost function to make it quadratic as well. Clearly, if you look at it as is, it's not quadratic, because there is theta, which is a variable, and the R, which is in a square, so it's not quadratic. But you can manipulate it to make it quadratic. And the final observation is that also the theta, which is a binary variable, here I'm writing that theta is in 0, 1. But if you say that instead theta is a binary variable which can be either -1 or 1, that's again something that you can express with a quadratic constraint. You can say theta squared equals to 1, which means that theta is either +1 or -1. So that's the trick that we are using here. And okay. I would say that this is probably the first technique for robust registration, for which you can get globally optimal solution with guarantees through the through the SDP relaxation.
Thank you very much. Yeah, that was a quite detailed answer. Yeah, really nice. Thank you very much. So I think we should switch to the next speaker. So maybe you can remove the screen. Thank you very much, Luca, for all these answers. It was really nice.
Yeah, and I invite everybody just to reach out if you guys have questions and so on. Reach out by email, but thanks for having me.
Thank you. So our next speaker was Joan Sola, who presented the Lee theory for the roboticists. So Joan, are you here?
Yes. Hello, everybody.
Hello. Perfect. Yes. So yeah, very nice talk indeed. So I will also start with a question of the Google Doc, and then again, if anyone in the end has any question, please feel free to ask. So first of all, a question by Federico. So Out of curiosity, have you ever explored different representations in your research, such as, for instance, dual quaternions algebra or spatial vector algebra? Do you think that regarding future works on Lie theory application to robotics, this is a topic worthy of investigation, or are there more crucial problems to solve? Namely, where do you think research should be heading?
We have, the question is long. I think I will ask you, Noemi, to repeat some parts.
Yeah, sure.
But we have been investigating a few groups, but the main work of this talk that I have given is to present the abstraction. So all that is in common to all these groups. We have rotations and translation, similarity groups, and also each one of these groups can be represented in different ways. For example, the rotations, you have the matrices or the quaternions. And for rotation and translation, you can go for the dual quaternions. So regarding the dual quaternions, for example, I am not super familiar, but we are trying to incorporate it to the library that we are coding because it has some advantages, but I'm not very familiar with that. The other parts of the question, Noemi, can you go again to the, I think there were like three parts.
Sure, so the last part was, do you think that regarding future works on Lie theory application to robotics is a topic worthy of investigation, or are there more crucial problems to be solved? And the last part was, where do you think research should be heading?
Okay, there are, so what I presented is very simple. It's maybe the first approximation one can have from all the corpus of Lie theory for the robotician. In particular, all the handling I do for uncertainty and this kind of treatments stops at the Jacobian. So it's kind of the first order linearization. And there are some works from, for example, Tim Barfoot that is dealing with higher order terms for dealing with uncertainty. And this obliges you to dig a little bit deeper into the theory and explore more the connections that exist between the group manifold and the tangent space, and in particular the Haus-Campbell equations and so on, that allow you to have a better propagation of uncertainty, for example. And then regarding, so I mean, there are things that can be investigated for the robotician. That means, for me, what do we have to bring from the Lie theory to the robotician? Because Lie theory is very old and it's huge and it's very complete. I don't think our goal is to improve this theory in any sense. This is the goal of abstract mathematics. But I do think there are some areas of this theory that are very useful for us. And maybe I just made the first step, not just me, but some researchers in robotics that are bringing Lie theory. Maybe there are more steps to be done. And the last part, where should research be heading? I guess you mean in this sense. I think it's already answered. It's understanding the theory. One thing that is it shocked me is that this theory is very old. The people who know are very skilled, but when you read papers and books, it's difficult to understand because information is scattered, notation is not homogeneous, and the background of the people who wrote these books and the target audience these books were written for is not us. So for me, for example, I had a difficult time in putting the pieces together. So the effort, I think, is this one, making sense of this theory for us. So translating some strange languages and some theorems, some concepts that are too abstract for us and bring them closer to our intuitions and our way of thinking.
Thank you. Yeah, I think this is a very important thing to manage to bring those geometrical methods to roboticians. Maybe related to that, we're also using sometimes Riemannian manifold theory. Can you a bit elaborate on the connections between these two theories, if you think that they're related, if this is the same process for the roboticists?
Yeah, interesting. Indeed, some of the problems we deal with estimation in robotics cannot be put in a group. For example, if you want to estimate directions of 3D vectors, so the set of unit 3D vectors is not a Lie group, but it defines a Riemannian manifold, which is the sphere in 3D. So the Riemannian manifold, it doesn't contain the notion of group, but it's there to exploit all the part of the calculus. So if you remember my presentation, there is the notion of group, which is something that when you operate it, it stays in itself. And then there is the notion of manifold. And the Riemannian manifold theory, it focuses mainly on the manifold part. And for example, I introduced the plus operator or the exponential map, which is a mapping that goes from tangent space to manifold. And in the Riemannian theory, this is called not the wrapping, I forgot the word, lift and retract, the retraction. Okay, so you are in the plane and you retract onto the manifold. So that operation is called retraction in Riemannian theory, and we call it exponential map in Lie groups. So there is a lot of connections, and I would say it's in some cases you have to go to Riemannian theory because Lie groups are not helpful, but most of the intuitions are the same. So I think these two fields are very much connected.
Thank you very much for your answer. I think, Luca, you have a question. I see that you have the hand raised.
Yeah. So, Jean, first of all, great talk. I watched the entire thing, like on the entire recording, and I loved it. I also plan, like, to share with my students, like, the write-up that you guys have. I think is very comprehensive, and you're right. It's kind of addressing a middle ground between applied math and robotics, which is very useful to have, actually. My question is more on the software side and Manif, right? So I wanted to get a little bit of the context or the vision that you guys have for that software, because you guys are well aware there are, like, a number of other things, like, in that domain, both on the robotics side, like, I don't know, I'm thinking about GTSM or CIRES, for example, and on the applied math side, such as Manopt, for example. Mm-hmm. So what's your vision for that? Where do you guys want to be, and what do you see as difference with respect to the existing libraries?
Okay, there's a lot of aspects. First one, let me tell you that I am the mathematical agent here and not the computer scientist, which is Jeremy DeRay. So he's got a vision for where this library has to be positioned in front of other libraries that are similar in a number of aspects. So having said that, I think we got a pretty good product, which contains, first of all, eigen-like, eigen, the algebra library. It's an eigen-like design with CRTP design. And it has a base class, which is the abstract part. And then its derivations are each one of the groups, okay? For example, this allows you to write abstract code. You can write code doing, for example, motion planning, and then you can particularize it in 2D or in 3D. But all the interpolations, if you can define splines inside the spaces, those spaces are abstract. And you can write code at that level. I think this is powerful. And then there are a number of questions that are difficult to solve. For example, one of them is what do you do with Jacobians? Okay, Jacobians can be defined left or right, can be defined from the vector representation of the group into the tangent space. For example, Google Ceres doesn't like proper Jacobians defined on manifolds because the operation of the optimization in the manifold is split into two parts. And so when you write a library and you want it to be used in different projects interfacing with other libraries, it's difficult to get one solution that is good for everything. For example, our Jacobians are compatible with what Ceres wants to do, but you need to trick it a little bit. They are not directly applicable, for example. But I don't know, there's quite a few aspects. The good guy to ask more about this is Jeremy, is the architect of this library. And maybe if I have a second, I will try to find one, where can I find this?
And I guess from what you're seeing, Jean, since you have been talking also about planning and so on, this is not going to be a library for state estimation or SLAM. It's going to be a library for optimization, right? It's going to be more general than state estimation.
Sure. This library. So I have been doing state estimation for years. So when I talk to an audience that this is useful, it's difficult for me to say it is useful for other topics because I cannot be so sure. So that's why the title is for state estimation. But I realize slowly that this is also useful for control, for planning, and it's probably going to be useful for any field that requires some modeling, some geometry, especially if you deal with optimization, where you deal with errors, increments, steps, all these infinitesimal parts. So this becomes useful. Maybe I restricted my discourse to estimation just to keep on the safe side from but I think you can use it everywhere. It's just mathematics.
Okay, thanks, John. Thank you.
Thanks you.
Thanks. So I see that we have a question in the chat, so maybe we take that one and then we switch to the next speaker in order to be a bit following the schedule. So Aditya is asking if you're using the Maple package and that dual quaternion can be referred as studied parameters. In general, when used quaternion representation are this equation are in general, when used quaternion representation are this equation algebraic. Yeah, I think you can read it on the chat.
Maybe, yeah, because I didn't.
Yeah.
Let me go to the chat. Okay. So the last question from Aditya.
Yeah, exactly.
Thank you. So quickly, are you using Maple package? No, never. I know because I was in a tutorial about Maple some months ago, and I put this question to the speaker, and he responded that Maple has nice packages about all these things and differential geometry, but I haven't gone into it. So that's the first easy question. So no, dual quaternions can be referred as study parameters in general. It's a strange question. When use quaternion representation, are these equations are in algebraic? I cannot tell. I don't understand very well the question, but most of all, I don't know enough about dual quaternions, and I never heard about study parameters, so I cannot go into this question. Sorry.
Okay, thank you very much. So we're gonna go to the next speaker, which is Taeyoon Lee. So Taeyoon, are you online?
Yes, hello.
Yes, hello. So maybe again, I will start with one of the questions of the Google form, and feel free to raise your hand or to ask it on the chat. So the first question is related to the practical implementation of the adaptive robot control algorithm that you presented in your talk. So regarding the parameter adaptation law you present, are there any measures needed to be taken in order to guarantee numerical stability of the parameter update? I believe positive definiteness and symmetricity of a matrix might easily be jeopardized due to floating point calculation, and implementing your algorithm naively without any additional consideration is prone to be unstable. Therefore, I ask the following: is some form of orthogonalization or projection strictly necessary in practice, and how will this be implemented exactly to avoid numerical instability?
Okay, I don't think I fully understand the question, but I think the question is mainly about, is there some maybe numerical integration error that actually defies the theory that actually says this differential adaptation equation on the positive definite matrix manifold actually incurs instability issue in practice. And yes, when I first deployed it in a real robot, I was also a bit worried about this issue. So first, I actually so I didn't just do the naive Euler integration on the positive definite matrix manifold, but I actually did actually the idea that John Sola just mentioned, the retraction map, was the exponential map like mapping using the tangent direction on this manifold. So that actually guarantees the parameters to always lie on the inside this manifold. But I also tried not using this retraction map, but I think the property of the natural gradient itself actually really preconditions the parameters well, and I've never experienced the parameters actually diverging outside the PD cone manifold. And yeah, still the step size matters, but I think the most important thing is that what kind of metrics or what kind of preconditioning you are using to really adapt your parameters on the manifold.
Thank you very much for this answer. Anyone in the audience has some questions? You can put it on the chat or raise your hand. Otherwise, I will go with the second question of the Google form. So, for the problem of geometric model identification, I would like to ask you if there are some disadvantage, for example, accuracy, when using the convex relaxation of the optimization problem instead of the original non-convex formulation.
I think so. Are you asking the disadvantage from using the original Riemannian distance or the original Euclidean distance? I don't know if I understand the question.
So I'm not sure if there are some disadvantages using the convex relaxation instead of the original non-convex formulation.
Oh, yeah. So yeah, we actually did a study on this in the paper actually, and yeah. The advantage is obviously the speed, and so we could, since this is just estimation, we can also check compare it empirically, right? Because we don't actually know the real optimal distance metric that can be used in our application. So in practice, the performance gain was minor. I mean, sometimes Riemann distance metric works better, or sometimes entropic divergence works better. And I just want to make a point that I think the choice of distance metric that I proposed in the paper, the specific choice does not actually matter as much. I think there can be a better metric defined on the PD manifold, but I just want to make a point that a class of metric that satisfies some kind of desired properties like invariance to affine transformation, I think this really helps a lot in the overall performance and generalization estimation. Yeah. I cannot really say that the convex relaxation is worse than the original Riemannian non-convex one.
Okay, thank you. So maybe just to take again a point that you just discussed. So in your methods, you're using the affine invariant distance, right? So which other distance you would be able to use for the symmetric positive definite cone, which would be the other one that could be exploited, and which advantage they will have, or you think that you say that you think that it won't change much, but yes, still there should be some reasons for that particular choice, no?
Yeah, we also considered other choices, but we could not actually find many other distances on the PD manifold that actually satisfy the desired properties, like the affine invariance. But we also have had a look on the Wasserstein distance, like distance metric, because it's actually well-defined distance defined on the mass density functions. But yeah, in the end, we found it hard to make it hard to realize actually convex relaxations, and also realize that it's not necessarily invariant to the affine transformations. So yeah.
Okay, thank you very much. That's really interesting to know. So I think if there is no more question, we can switch to the next speaker. Thank you, Taeyoon.
Thank you. Thank you for having me.
Thank you. So the next speaker was Bruno Adorno, who presented a talk entitled Complex Robotic Systems, Modeling, Control, and Planning Using Dual Quaternions Algebra. So Bruno, are you here? Yes.
Yes, hi, hello.
Hi. So I will also go first with one question of the Google Docs. Regarding the challenges associated with future research on dual quaternions algebra and its application in robotics, do you think of any foreseeable limitation that could hinder its development or even render this approach unpractical for some specific situations? In other words, do you believe that there will be some applications in which classic representation will remain advantageous?
Well, this is a great question, and it's a very deep one. Well, in principle, everything that you can do about geometry, in principle, at least, could be solved by using different representations. So it's just a matter of, in some cases, of practicality. When we think about dual quaternions, which must separate the representation from the language itself. Dual quaternion algebra is a language that enables us to reason about geometry. So in that sense, I would say that I cannot see for a moment a place where conventional representations and conventional algebra would outperform dual quaternions in general, but the converse may be the case as well. In some cases, dual quaternion algebra may be equivalent to, to regular representations, and in some cases it can be more advantageous. But still, there are still some parts that dual quaternion algebra in general may have some advantages because the theory is not so well developed. So in that sense, in that regard, I would say that it depends on the interest of the community in developing the mathematical tools so that they are available. If this is the case, there is no principle that prevents dual quaternions from being used in whatever scenario where geometrical reasoning must be done.
Okay, thank you very much. That was a quite interesting answer. I see that there is no question in the audience. So if someone has a question, really feel free, raise your hand, write it on the chat. And maybe to follow up on what you just said. So in your talk, you were talking quite a lot about modeling, control, and planning. What about learning with dual quaternions?
Yeah, this is a very interesting question. And well, I will provide an answer similar to John's answer in the sense that I'm dealing with it's safer from my point of view because I'm not an expert in learning. But yeah, definitely, I think that dual quaternions in general can be used for learning because first, as an algebraic tool, it's quite easy to operate on them. And we must recall, when we talk about dual quaternions, we have unit dual quaternions, which are similar to homogeneous transformation matrices. They represent rotations and translations. But also, if we do not restrict ourselves to unit dual quaternions, we have a whole algebra to work on. So we can represent, for example, several geometrical primitives, which can be used in learning algorithms to geometrically reason about the world. It's easy to write constraints on dual quaternions. For example, if we take unidual quaternions, which is a specific instance of dual quaternion algebra, unidual quaternions are also a Lie group, so you can use all tools from Lie theory, and that's it. So in principle, you can use it for learning algorithms, and I cannot say much about what would be the advantages of doing so, specifically for the case of learning, mainly because I haven't worked on that topic. But in terms of mathematics, of course, there are several advantages of using dual quaternion algebra. For example, if you use rotation matrices and position vectors or homogeneous transformation matrices, so you can form a group, but this group is very redundant in the sense that you have a lot of parameters and you have to enforce several constraints in order to obtain again the 6-dimensional manifold of Euclidean motions, right? So in case of unit dual quaternions, you have the smaller set that forms a group. So it's very economic in terms of computational cost. So this is a clear advantage over other representations. But what I like the most is not exactly the fact that they are computationally efficient, but as a language itself, it is very powerful, I would say.
Okay, thank you very much. So I think we should definitely go, I mean, the machine learning people that are here have a look at dual quaternions in the learning frameworks. Yeah.
Great.
So you have a question in the chat from Philip Marek. So why do you think dual quaternions aren't more prevalent in robotics today?
Well, this is a very good question. And interestingly, dual quaternions are also very old. As Lie theory, they were developed in the 19th century. So the first representation that came up were quaternions. So after that, Clifford invented the so-called biquaternions, which then studied, borrowed, and started the geometrical reasoning that we know today. So this is a development done by Study, Clifford, and Hamilton on the 19th century. And after that, when Hamilton started working on quaternions, he started with the idea, which in my opinion is not so fortunate. He introduced the scalar plus vector notation. I prefer other kind of notations like the hypercomplex one, where we treat quaternions and dual quaternions as extensions of complex numbers, but without using the scalar plus vector notation. And maybe one of the reasons that I don't like it because first, it's not, it mix several things that I prefer not to, but also because Gibbs, when interacting with Hamilton, realized that the vector part was interesting, and then he developed the vector algebra that we know today, that finally gained some momentum, and because it was very practical, so people from engineering and applied fields decided to use vector algebra instead of quaternion algebra and that earlier representations. But then in the last 30 years, more or less, some physicists discovered that for some things that you want to represent, vector algebra becomes limited in terms of expressivity, how you can express your geometrical ideas. So they started to work again on that topic. And I think that after that, more tools started to become available. And then in the last 10, 15 years, dual quaternions have gained momentum again. So now we have more tools. We were talking about, John mentioned about introducing dual quaternions in their library. So we've been developing a library called DQ Robotics, in which we implemented tools for robot modeling, control, several different controllers, such that we can make that representation more popular. Because indeed, I think that it's not so widespread because before there weren't too many available mathematical tools. The theory was still incipient for more applied fields such as robotics. And then after we figured out the theory, the application of the theory, there were no available tools, computational tools. But now we are developing those tools. So I believe that dual quaternion algebra in general will be more widespread, hopefully.
Thank you very much. So Federico asked the question that is related to the one of Philip. I think you basically just answered, but I will still ask the question, and then we go to the poster session. So Federico is asking, what do you think is missing to make dual quaternions more popular in the community? So I think it's yeah, what you said at the end. But go ahead.
I think I partially answered the question. It's a matter of making more tools available, making the theory widespread so people can understand it. And I also would like to borrow one of the things John said in his talk. So the first available texts on dual quaternions were very focused on the mathematics, and the theory was scattered, and it was difficult to assemble them together in order to have a coherent text that a beginner could understand. And now, because more people are aware of this tool, people are starting to write papers on that, and it's becoming easier and easier to understand it. So it's just a matter of time now.
Thank you. Thank you. That was a quite nice answer also. Thank you for all those precisions. It's a really nice discussion. People agree on that on the chat as well. So thank you very much.
Thank you too. And finally, I just want to thank you all for bringing this up. This workshop, in addition to being very interesting, I think it's very much needed for the community, and congratulations. Thank you for the invitation.
Thank you very much for accepting to give the talk and for being here today as well. Thank you. Okay, so we're going to go to the poster session. So I hand over to Leonel for it.
Okay, thank you, Noemi. So let me tell you briefly about how we're going to proceed now. We have 7 papers for the first poster session that are mainly split into 2 groups. So the first group is actually about some set of papers that brought some geometry awareness into learning. So that's actually pretty interesting. The second part of the poster session is 4 papers that are actually combining some optimization techniques with geometry as well. So how we're going to proceed here is that we're going to have the first 3 talks regarding to learning approaches. Then we're going to try to ask the audience for some questions for the speakers. And after that, we're going to present the remaining 4 papers plus another short Q&A for the remaining papers. So now let's get started.
Okay, so good morning everyone, and today I'm going to present our recent work on optimizing sequences of probabilistic manipulation skills that are learned from demonstration. It's a joint work with Lucas from University of Stuttgart and my colleagues from Bosch Center for Artificial Intelligence. So in this work, we want to enable end users such as factory workers to teach flexible robot manipulation skills fast, and they should be adaptive to new scenarios, and we want to enable them to compose those skills into complex manipulation tasks. And if you look at the existing approach for motion and task planning for manipulation, and you see that many approaches focus on discretization of state or action space, and normally a precise simulator are required for both training and learning for the skills. Also, when they want to compose such skills, you also design manual tuning and ad hoc rules. So in particular, we extend the learning from demonstration framework. So each skill is represented by a general task parameterized hidden semi-Markov model, which can be learned from a few demonstrations normally. And then in this work, we extend this framework by introducing 3 task parameters, which we find out to be particularly useful when you want to represent movable objects. And then we introduce the notion of transition skills, which, for example, rotation and translation of objects. And then we introduce the notion of condition and effects that can model the statistic property of a skill. And in the end, we propose a measure of execution confidence when you have a sequence of skills as a manipulation task. And in the end, we propose a method to maximize such confidence by optimize the set of 3 task parameters. And I want to point out that all this framework doesn't need any simulation. So we evaluate this method over a set of 5 skills, for example, grasp side, grasp top, and translation, and insertion, and dropping skills. And we evaluate when and where transition skills can be used to improve the confidence of a manipulation task.
Thank you for attending this presentation. My name is Hadi Bek Mohammadi. I'm a PhD student at Bosch Center for Artificial Intelligence. Today, I would like to present our paper on Riemannian manifold learning for robot motion skills, which combines different aspects of motion skill representation from a geometrical perspective. So why we should really consider the manifold geometry learning, specifically Riemannian geometry, in order to do learning from motion skills. The most important reason that made us think about using geometry is the amount of information that can be gained by capturing the geometry of the data. And this information can be used to facilitate the learning process or even generalization and learning a complicated task. Obviously, there are several restrictions in capturing the geometry, like the high dimensionality of the ambient space. Therefore, we have to make some assumptions. For example, the data does not cover the whole ambient space, so the data is sparsely distributed. Or the second one, the data lies on a manifold in a low-dimensional latent space. And the most important assumption, which is the latent demonstration data lies on a Riemannian manifold. But actually, how do we capture the geometry? Different people might have a different interpretation of the geometry of the data. And sometimes the word might be a little bit misleading. In our work, when we mention geometry, we mean exploiting the uncertainty. The uncertainty simply means the area with more data has lower uncertainty and other way around. So just to be clear, the uncertainty itself is not directly interpreted as geometry. Imagine having the latent space with latent data representation as this image. Now we can see the area with low uncertainty shows where the demonstrations have happened. And we can use this information to our favor to capture the geometry of the generalized motion skills to produce more similar motions, which we will talk about in a minute. First of all, the Riemannian manifolds are described by Riemannian metric tensor, which is actually the collection of smoothly varying inner products defined on the tangent space of the manifold. And we define it like the M tensor on the slides. We also call it the pullback metric. So to deal with our assumptions regarding Riemannian geometry, we need two important components. The first one, the latent representation Z, and the second one, probabilistic mapping between the latent space and the ambient space, which is also helpful to calculate the pullback metric from the tangent space. These two assumptions are guiding us to use generative models, and specifically variational autoencoder, which is close fit to our assumptions, as you can see here. Now, having learned the necessary components for our manifold, we can think about using geodesic to reproduce motions. The geodesics are shortest paths on the manifold between 2 points, and they are the equivalent of straight lines in the Euclidean space. In our case, that the latent codes are actually the encoded motion trajectories from circular motion demonstration. Following the geodesic can give us a motion similar to circular demonstration that is somehow generalized and inherent in to the length manifold. The length, as you can see, is defined based on our stochastic function and eventually related to our metric tensor. By minimizing this length, we achieve a local geodesic, as you can see in the left plot. And the right plot also shows how the variance uncertainty or the manifold looks like in the latent space. So in summary, we exploit the Riemannian geometry of the data to learn robotic skills from demonstration. We encode the geometry of the demonstration data by using a variational autoencoder, and finally synthesizing motion by exploiting the geodesics. In this picture, you can see a different manifold trend using demonstrations, which are the positions of the end effector, and they are being used to generate geodesics that represent similar motion as demonstration, which is shown as the blue curve on the right side of the image. The way that the length is formulated gives us the flexibility to add more constraint without training the network again. We can add abilities like obstacle avoidance on the fly for the new geodesic by modifying the length formulation. You can see in the result the geodesic that considers the obstacle, which are the blue curves, they successfully avoided them. And the green ones, which are the simple geodesics, they did not care about the obstacles. In the future work, we consider including dynamic obstacles and orientation of the end effector. Thank you for your attention. I would be happy to answer your questions now.
Hello, I'm Sylvain Chevalier, and I'm very happy to be part of this IROS 2020 workshop. I'll present a work called Extending Riemannian Brain-Computer Interfaces to Functional Connectivity Estimator. This is a joint work with Marie-Constance Corsi, Florian Iger, and Camille Nous. Brain-computer interfaces are especially useful for assistive robotics, and they are demonstrating major advances in exoskeleton control with implanted electrodes. While being more modest, using EEG-based BCI, it is possible to achieve wheelchair navigation control or limb exoskeleton control. Still, there is some limitation. The first one is called BCI inefficiency, because the state-of-the-art algorithm fail on 20% of the subjects. The other problem is that there is a specific geometry of the EEG, because linear and Euclidean method do not give very good results. And if you try to apply out-of-the-box machine learning algorithm or deep learning methods, you will not have very good results. But there have been very good results obtained with geometric method for BCI. And it seems that using covariance matrices, the geometric methods are able to capture some invariance of the EEG signal. And while working on SPD matrices, it is possible to define some very robust and effective classifier, such as minimum distance to mean or classification in the tangent space. These geometric methods and so-called Riemannian BCI are now the golden standard in BCI task. Still, the covariance matrices is only one possible estimator, and there are other estimators for functional connectivity that are described in a rich literature. These information are very complementary to covariance, and we could cite estimators such as correlation, coherence, or phase locking value. It is possible to use this estimator directly to estimate or to classify trials, but it yields very low results. Still, the carried information is very heterogeneous. That is, the diversity with respect to the covariance is very important. So we show in the paper that if more than 50% of the misclassification trial by covariance matrices are correctly classified with the functional connectivity estimator. So brain-computer interfaces are very promising controller for the robotic, and geometric methods are already the current state of the art. And it seems this is because covariance matrices capture very robust invariant for the control of exoskeleton or mobile robots. In this contribution, we show that functional connectivity estimator could play a very good role to improve the robustness of this estimator and of the classifications. There is many research leads. It's possible to try some extension and application using Hermitian positive definite matrices. Also, using joint optimization or product manifold is a very good lead of research. And there are already work on geometric interpolation on regression for robotic controller that are quite promising. So thank you very much for your attention, and please enjoy the rest of the workshop.
Okay, thank you all. Thank you, Meng, Hadi, and Sylvain for such a nice talks. So we have already a question in the chat. I think this for Hadi. So the question is, do you think there will be any benefit in collecting manipulability ellipsoids alongside n effector position in the demonstration data, which is later characterized as a Riemannian manifold. So I think Hadi is online.
Yeah, do you see me?
Okay, cool. Yeah.
Yeah, of course. I think like any kind of like right now we are in a very like first part of our experiments, and I feel like using manipulative ellipsoid can help like having a better understanding of the input space that we have. So like right now we are moving toward using the quaternions, and maybe later we are also having planned to use these manipulative ellipsoids that may be helpful. But I don't know yet, but it might be, yeah.
Okay, thank you, Hadi. Is there anyone that may have a question for the speakers? You can unmute and go ahead. Okay, so I do have a question for Sylvain for the last talk. So usually people that handle this kind of SPD data for classification, one of the usual things to do is that they may argue also that a Cholesky decomposition of data may also work and may do the job. And I was wondering if you explore also this in your work, or if you just directly use the SPD cone for your work.
Oh, thank you for your question. I didn't understood the part of the mixing. You say you could use the yeah, sorry.
Sorry, no problem. So actually, I mean, for example, when it comes to represent covariances, so people can understand this as a point on the SPD manifold, right? But some people may argue that you can also just handle this data using the Cholesky decomposition. So just this is composition and try to work with it. So I'm not sure if you compared this in your work and you tried to maybe give it a try before. I'm just curious about this.
Yes, thank you very much for your question. This is very interesting, and in fact, yes, we try some Cholesky decomposition, and yeah, it works, and but it seems that it could depend on the kind of implementation you want when you work on the on the SPD matrices. There are several toolboxes available. Some of them use Cholesky decomposition. Other use directly eigenvalue decomposition, and it gives good results. Most of it's mostly a problem of stability coming to the results. The brain signal is very noisy, and the signal to noise ratio is very bad. So using Cholesky decomposition or other kind of tricks is really important to achieve robust and reproducible results. So yes, thank you.
Okay, thank you, Sylvain. Any other question from the audience? Okay, I'm afraid no. So I guess that we can now move on to the second part of the poster session, which is related to the optimization-based techniques.
Hello, IROS 2020. I'm Matthew Gamo, and on behalf of my colleague Philippe Merich and our advisors, I am pleased to present our work on inverse kinematics as low-rank Euclidean distance matrix completion. We are with the University of Toronto's STARS Laboratory and the University of Zagreb's Lamor. Given a model F of a robot's forward kinematics and a goal position or pose W in its workspace, the problem of inverse kinematics asks us to determine a set of joint angles theta that position the end effectors on the goal. When a closed-form solution is unavailable, optimization-based methods are commonly applied. Additionally, a variety of heuristic methods, like fabric, can be used. However, Rapidly and reliably computing this essential step in the motion planning pipeline remains a challenge for robots with many redundant degrees of freedom and complex branching structures. To address these challenges, we look to prior work on modeling kinematics with distances between points on a robot that are invariant or bounded under joint actuation. This distance geometric approach has been used in conjunction with algebraic solution methods on a variety of low-dimensional spatial mechanisms. Our work formulates this description of inverse kinematics as a Riemannian optimization problem, allowing us to efficiently and accurately solve problems with many degrees of freedom. Our approach hinges on a symmetric matrix called a Euclidean distance matrix, or EDM. Given a set of n indexed points, the entry in column I and row j encodes the distance between the ith and jth points. For a simple two-joint planar manipulator with points fixed to its joints and end effector, we can describe the manipulator's feasible configurations with constraints on the corresponding EDM. For example, the fixed joint lengths correspond to exactly known elements in the EDM. Similarly, symmetric joint angle constraints become bound intervals on distances between points adjacent to the bounded joint. This relationship between kinematic constraints and EDM elements provides a procedure for transforming a broad class of inverse kinematics problems into partially known EDMs for a variety of manipulator types. Fixed linked lengths provide exactly known distances, angular constraints provide bounded distances, and goal poses provide exactly known distances from end effector points to the robot's fixed base. Now that we've established a procedure for transforming a robot's kinematics into a set of constraints on distances between points, we will briefly summarize our approach for completing this partial Euclidean distance matrix. We use a recent approach for EDM completion that accounts for the low rank of our solution caused by the 2D or 3D nature of physical inverse kinematics problems. Since the distances between points are invariant to rotations and reflections, a solution is actually an equivalence class of all sets of points related by an orthogonal transformation. This approach uses optimization over the Riemannian manifold of all such equivalence classes. Combined with a standard procedure for extracting the angular configuration from this set of points, we have produced a full inverse kinematics pipeline. We have conducted a number of preliminary experiments that compare our method with a variety of algorithms on a number of common robots, including the UR10 and a KUKA arm. These box and whiskers plots demonstrate that our methods, in blue and yellow, exhibit considerably lower position error on high degree of freedom planar tree manipulators. Our Python implementation also runs quite fast for an approach that has not been tuned for performance. In these plots, each row shows the convergence of a different algorithm on a toy 6 degree of freedom manipulator with position goals. Our algorithm is the only one that is able to reach the correct solution. The other three methods all converge to the same local minimum. Returning to our two-joint manipulator, we are also experimenting with the addition of spherical obstacles. This involves adding a new point for each obstacle and ensuring that the distance from the obstacle to each mobile point on the robot is bounded from below by the object's radius. The robot's immobile base has a known fixed distance from each obstacle. This approach is an elegant unification of a robot's task and configuration spaces, which we hope will lead to simple and efficient algorithms for complex planning problems. Finally, we are looking into semi-definite programming approaches and algebraic methods for solving our distance geometric formulation of inverse kinematics. Thank you for your interest in our work. Be sure to keep an eye on our GitHub repository for further developments and code releases.
Hi everyone, thank you for your interest in our research. This presentation aims to give a summary of our article entitled Improving the Iterative Closest Point Algorithm Using Lie Algebra. I'm Maxime, and together with my co-authors, we are part of NORLab at Université Laval in Canada and Institut Pascal at Université Clermont-Ferrand in France. Nowadays, many applications, such as self-driving cars or environmental monitoring, require accurate maps of the environment to complete their tasks. By using some mapping algorithm, such as ICP algorithm, we can obtain these maps as the one shown here. However, algorithms like ICP are prone to drift in the estimate pose. To minimize these drifts, some researches were done such as Bama and al. Based on this work, we add our own angular penalty term to the ICP construction. Our penalty term is built using Lie algebra with the rotation coming from the prior. In that way, the ICP process is penalized and leads to more accurate maps and localization. We choose to develop our penalty term with Lie algebra over Euclidean space to avoid rotation singularities, and also because this implementation needs few parameters. Before going into the computation of our penalty, let's quickly review the concept of Lie algebra. SO3 is defined as a group of 3D rotation matrix, and SO3 is a special orthogonal group. A Lie algebra is a tangent space of the Lie group at the identity element, as shown in this picture. In the Lie algebra, the rotation is defined as the vector phi. With this representation, it's possible to do some conversions between these two groups by using the exponential map of a matrix. These concepts will be used to compute our penalty term. The special orthogonal groups gives us a basis for the rotation phi that is a vector space, hence giving all the classical tools of probability that we wouldn't have in the 3D rotation matrix group. All of these concepts are more detailed into the Barfoot paper cited. Our angular penalty term is defined according to two terms, E theta and the covariance sigma theta. To compute them, we use the noise prior rotation matrix and the ICP rotation matrix. With this information, we can express the rotational error E theta, where beta is computed according to this rotation matrix. By doing some approximations and developing our equations, we can find this rotational error in the Lie algebra. Then, we use the Mahalanobis distance of beta from the origin in the Lie algebra to find our penalty term. To validate our angular penalty term, we did some experiments. First, we use a Wardog platform coming from ClearPath Robotics as shown in this left picture. This platform were used with the IROS'20 RoboSense LiDAR and an inertial measurement unit. During this experiment, the robot was performing high-velocity trajectories on the snow. We also used the SLAM evaluation benchmark from the Kitty dataset to evaluate our work. These two pictures present a part of our preliminary results done with the Wardog experiments. On the trajectory computed without the penalty on the left picture, two breaking points can be seen, meaning that the ICP converge to a wrong solution. With the Lie penalty used on the right picture, these breaking points are avoided. In this case, our penalty term pushes the ICP to converge quicker to the right solution while avoiding local minimum. In this article, we propose a novel method to penalize the rotation of the ICP algorithm with Lie algebra. Using preliminary results, we showed that our method leads to increased accuracy and stability of the ICP. Future work will focus on improving this penalty by taking into account the noise in the angular rate of the IMU. Other experiments in different environments will be done with a ground truth reference provided by 3 theodolites. Thank you for your attention. I hope you like it, and if you want additional details, don't hesitate to read our paper or contact us.
My name is Kira, and I would like to present the extended abstract with the title CMAS and Many Manifolds for Optimizing Robotic Manipulation Tasks. One problem in robotic applications is the parameterization of skills, such as parameters of a controller. Hereby, the aim is to execute the task safely, but also efficiently. This problem belongs to a black box optimization problem and can be solved for Euclidean parameter space. But the parameterization is given more generally by a Riemannian manifold. Therefore, we propose an extension of the optimization method CMAS to Riemannian manifolds. original CMAS works by sample parameter choices theta from the domain by a Gaussian distribution and scaled by a so-called step size, which denotes the amount of exploration. Zeta is then evaluated by the objective function and sorted by its objective values. The mean is updated towards the best performing ones, as well as the covariance matrix and the step size are updated. To convert CMAS from the Euclidean space into a manifold, mainly three operations are needed. To transform a point from the tangent space into the Riemannian manifold, the logarithmic map is needed. When applying the reverse transformation, so manifold to tangent space, the exponential map is applied. Another operation called parallel transport is useful to transform vectors from one tangent space to another, but while keeping the inner product constant. When transforming CMAS from the Euclidean space to Riemannian manifolds, some operations need to be adjusted. The first step, sample parameter choices by a Gaussian distribution, stays as in the original CMAS, except for the mean, to be represented in the manifold. The parameter choices are represented in the tangent space and need to be transformed to the Riemannian manifold by previously explained exponential map. Those parameters in the manifold are then evaluated and sorted as in the original CMAS. The mean update differs from the original CMAS. When using the same update rule as in the original CMAS, the resulting mean would be defined with respect to the old mean. However, the aim is to compute the mean with respect to the new mean. This is done by an iterative Frechet mean, where the mean is approximated over multiple iterations. The covariance as well as the step size update is computed as in the original CMAS, except for these elements of the covariance matrix and also the step size, which are computed in the old tangent space. They are parallel transported from the old tangent space to the new tangent space. In order to evaluate CMAS on Riemannian manifold, two different experiments are conducted. The first one takes place in simulation. It adapts the orientation of an end effector while moving to different poses, such that the joint velocity is minimized. The motion profile experiment finds the optimum faster and the variance is lower when our approach is applied instead of the original CMAS. The aim of the second experiment on the rear robot is to insert a peg into a hole by optimizing the pose of an end effector, such that the contact force is minimized. Here the number of successfully inserted samples lies at around 2/3 when using this recent approach, whereas applying the original CMAS obtains a success rate of less than half of the samples. There are mainly three relevant papers which can be compared to this approach. Comparing this approach to the geometry-aware Bayesian optimization, the main difference lies in the approach itself. There are two other approaches which transform CMAS through Riemannian manifolds. One proposes a framework which extends any stochastic derivative-free optimization algorithm to Riemannian manifolds, and also tested the framework on CMAS. And the other one extends CMAS to Riemannian manifolds to be applicable on 3D image reconstruction. But both approaches update the mean by a weighted sum in the tangent space, instead of an iterative approach. Overall, CMAS on Riemannian manifold outperformed the original CMAS in both conducted experiments. If you're interested in more information, you can take a look at my master thesis. Thank you for your attention.
My name is Sander van Rooyen. I'm a PhD student at KU Leuven, and I'm going to talk about coordinate invariant trajectory shape descriptors, or invariants in short, and how to calculate them efficiently in an optimization-based way. Coordinate-based trajectory representations depend on arbitrary choices such as the reference frame, reference point, and execution style of the demonstrator. Invariants, on the contrary, are independent of these irrelevant choices. They only model the shape of the measured trajectory. That's why they have better generalization capabilities. 3D point motion can be described by the Fresnel invariants, which are a result of classical differential geometry. Our group also proposed the extended Fresnel invariants and the instantaneous screw axis invariants to describe full three-dimensional rigid body motion. The high generalization capabilities of invariants have been demonstrated in a programming by demonstration application where a demonstrator learned a robot to port T from only a single demonstration. An important concept of invariants is the moving frame in which the invariants are expressed. The generative equations are a set of differential equations that describe the motion of this moving frame in function of its invariants. Given the initial moving frame and the invariants, we can always fully reconstruct the corresponding trajectory. Closed-form formulas for the calculation of invariants are available, but they rely on higher-order derivatives of measured trajectory coordinates. This results in an amplification of measurement noise. Another problem with the analytical formulas is that sometimes the invariants are undefined. For example, distortion when moving along a straight line. This results in singularities in the analytical formulas. In this slide, we demonstrate the result when directly calculating the curvature of very noisy measurement data of a 2D point motion. As seen in the bottom graph, the measurement noise gets amplified in the calculated curvature, yielding a result that is not useful in practice. The idea of optimization-based calculation is to find a new trajectory close to the measurement points that has smooth invariance. Here, the yellow points in the top graph represent the newly found trajectory, and the bottom curve the corresponding curvature in function of arc length. We briefly discussed the optimal control problem that is used in the optimization-based calculation of invariance. The first term is a reconstruction error, which tries to match the newly generated trajectory as close as possible to the measured coordinates. The second term is a regularization term, which penalizes non-smooth invariant signatures. The dynamics constraints integrate the generative equations, and they also preserve some properties like the orthonormality of the axis of the moving frame. The initial constraint makes sure that these properties are met for the first stage. In this slide, a sketch of the numerical optimization algorithm is given. First, we calculate the exact KKT system of the optimization problem at the current iterate. Then we check the positive definiteness of the reduced Hessian. This is important to guarantee that in the line search at step 6, we encounter an acceptable next iterate. This is commonly done in line search methods. At step 5, we want to calculate the search direction by solving the KKT system. In our case, this is by far the most time-consuming step, so it is here that we can achieve a huge performance gain by exploiting the problem structure instead of just using a general sparse solver. The structure of the KKT system is given in this slide. For completeness, we also give the formulas to calculate the block matrices appearing in the KKT matrix. The structure of the KKT system is exploited by recursive factorization that is related to the recursion used in a linear quadratic regulator in optimal control. We make use of the cited implementation. The requirement for this implementation is that the reduced Hessian of the optimal control problem is positive definite. This is not a problem because, as previously mentioned, this is required by the line search anyway. In addition, this implementation can also be used to test the previously mentioned condition. The obtained factorization can then later be reused as illustrated in this slide. The method is implemented in C code and makes use of BLESVIO, a high-performance library for matrix operations on small-scale matrices. First results of factorization of the KKT system related to the optimization-based calculation of Fresnel invariants show promising potential. a speed up of a factor 40 is achieved as compared to state-of-the-art general sparse linear solvers. In the future, we will include equality end-state constraints and inequality state constraints in the solver and investigate whether the algorithm can be used for fast optimization-based motion planning. Finally, I want to thank you for your attention and don't hesitate to contact me if you have any questions.
Okay, so thanks to our speakers for their talks. Are there any questions about those 4 talks in the audience? Feel free to ask, to unmute and ask, or ask them on the chat is also fine. So maybe in the meantime, I will start with one question. So for Philip and Matthew, so I think both of them are here, right?
Yeah.
Yes. Okay, perfect. Hi. So I was wondering, you're presenting an inverse kinematics, which is not based on Jacobian. So isn't that there you can add constraints more easily? So I was wondering in general, how does this compare with the classical Jacobian-based inverse kinematics and the null space that we usually add there?
Okay, so I guess in our initial preliminary experiments, what we've noticed is that our method outperforms Jacobian-based methods when multiple end effectors are present. So for kind of these more complex mechanisms where you have kind of branching kinematic chains, our method seems to do quite a bit better, even with joint angle limits. However, what we've seen also is that the Jacobian methods are generally a lot faster when working with commercial manipulators such as, I don't know, the UR10 or the KUKA or the shrunk arms. I think this is partially due to the amount of actual spatial constraints that exist in the problem. I think the distance geometric approach is better when more distance constraints are present, when the problem is more highly constrained. But again, it also very much depends on how the problem is initialized, which we also think is kind of an advantage of the Euclidean of the distance geometry approach, because there is an interesting way to initialize this problem by kind of guessing what the bounds are on the unknown distances and sampling the initial matrix within those distances, and we saw that this in fact causes kind of faster convergence. Maybe I don't know. Maybe Matt can add something here if I missed something.
Yeah, the only thing I'll add, I think Philippe said most of what I wanted to say. But also when using just like the traditional control like Jacobian like closed loop inverse kinematics methods, it's really dependent on having a good initial guess. So we actually only sort of had competitive success rates when using like a full Hessian in the solver for the angular based one we were comparing against. So that's another thing to consider.
Thank you very much for your answer. So I see that we have another question in the chat for Lander. So the question is, have you looked at benchmarking your solver versus other solvers that exploit the Markovian structure of optimal control problems, such as HPMPC or HPIPM?
Well, actually, we do something very well, we do something very similar to HPIPM. So the recursion we use is also available as an option in HPIPM. But the difference is that HPIPM is a QP solver, and we are really looking at at a nonlinear programming solver. So it actually exploits the structure in the same way, but it like HBIBM doesn't have the line search method that we use.
Thank you. So I hope, Brian, this answers your question. Do we have any other question in the audience for the speakers? Okay, so if this is not the case,
Okay, then, so I guess it's time for a well-deserved coffee break for all of us. We're gonna see, okay, I think that there is another question from Bruno. Maybe we should address it before going for the coffee break.
Yes.
Philip, would you like to answer it, please?
Yeah, I can. Do you want me to read it or just to kind of answer?
And you can directly answer it. I think it's fine.
Okay, so in your presentation, you showed that your message reached the global minimum noise. So our method definitely doesn't always find the global minima when it exists, but what we've seen is that it definitely does have different kind of convergence properties than joint-based methods. And also what we, I think for future work, what we find maybe an interesting approach is that basing inverse kinematics and distance geometry actually allows us to use convex relaxations. So, and Matt might want to say more about this once I finish, but basically there has been use of these convex relaxations such as semi-definite programming for similar problems, for similar distance geometric problems such as molecular confirmation. And just to kind of get into your second part, is it possible to recast the problem as closed loop inverse kinematics? Yes, it is. And actually, I think there is there is a paper that does something in that manner. I don't remember who the author is, but it's from 2019, and they use kind of these distance constraints and generate a Jacobian from those to kind of generate to basically to do like a closed loop inverse kinematics or end of or operational space control. I think it's an animation paper though, so they have different requirements. So they're more kind of they use spherical joints and they have less kind of they don't have the same types of constraints that you'd find in robotics. Yeah, Matt.
Yeah, I think also with regards to the closed loop inverse kinematics question, there's I think like a few decades of research into like multi-body dynamics simulation with constraints of this kind. So I think we could probably look into that field for some ideas and a good way to implement closed loop controllers and understand those dynamics.
Thank you for the question. It's a good question.
Thanks.
Thank you, guys. Thank you, Philip, Matthew, Maxim, Kira, Lander, everyone. So we are still behind the schedule. I think that's fine. I think that actually I've enjoyed a lot all the discussions and questions out there. For now, let's gonna take a coffee break. We're gonna start again in 15 minutes from now. So see you all later.
Okay, I think we can start again. Welcome back, everyone. I hope that all of you could get some coffee. So now we're going for the second part of this workshop. So we have a second Q&A session with the remaining speakers, then a second poster session, the panel discussion, and finally we will give the award for the best workshop paper. So first of all, the second Q&A session. So our next speaker is Subrachil Bhattacharya. So his talk was about planning and control on Riemann manifolds with boundaries. So as previously, we have some questions on the Google form, and also you're very welcome to ask questions. You can raise your hand, you can unmute and ask, and you can also ask the questions in the chat. So I will start with one of the questions that we had on the Google form, and really feel free to ask afterwards. So the first question was, in the slide 11, you show that the path resulting from S-star search closely matches the geodesic path. Is there any formal relationship between these two?
Hi, Naomi. Thanks for the question.
Hi.
So I guess we can show that as the size of the discretization goes to as it becomes smaller, the paths, the length of the paths becomes they kind of approach each other quadratically fast. So we have formal proof of that. So I guess if that's what I believe that's what the question is asking. So that's the kind of the theoretical proof that we have. So it of course, if the discretization is too coarse, then it's not representing the manifold well enough. Then there will be big difference between the path being found by the S-star search and the actual geodesic path. But as the discretization goes, as it goes infinitesimally small, then they essentially match exactly.
Okay, thank you. Thank you for that answer. Anyone else has a question, maybe in the audience? Feel free to ask. Otherwise, I will go with the second question of the Google Doc. So, may you please provide some details regarding the computational cost of the S-star search method?
Yeah, sure. So I didn't mention that, but in the talk, but the computational the complexity is same as Dijkstra. So if you so it's n log n. So if you assume uniform degree for each vertex, each zero simplex is connected to, on an average, same number of other zero simplexes. So the complexity, the algorithm is very similar to Dijkstra. It just kind of has this kind of open list that kind of grows in all directions relatively uniformly. So the complexity, so it's n log n, where n is the number of vertices or zero simplexes. But then the thing is, because we have simplexes instead of just edges, for each simplex, the amount of computation is higher. So so for each of those simplexes, the amount of computation grows exponentially with the dimensionality of the simplex, and that's actually very similar to what happens in, say, Dijkstra. So that's the course of dimensionality, right? So bottom line is the complexity is same as Dijkstra search. It's n log n, with n being the number of zero simplexes.
Thank you for the precision.
So there are a lot more details on the complexity analysis in the paper that I mentioned, the reference, and if you're interested, yeah, you can find more details in the paper.
Thanks. So yeah, I will go to check the paper for more details. Thank you for your answer. Anyone else has a question? Can feel free to ask. You can write it on the chat. You can unmute and ask. Otherwise, I will thank Subrachil again for the nice talk that you gave.
For organizing the workshop.
Thank you very much. And we can go to the next speaker. So the next speaker was Maxim Lekachev, who presented a talk entitled Planning for High-Dimensional Robotic Systems by Solving Problems in Low-Dimensional Manifolds. So Maxime, are you here? I think I don't see you on the chat. Okay, so it seems that Maxim is not with us for now. So maybe if he comes, we'll come back to him later. Otherwise, go to watch his talk on the YouTube channel or on the IROS'20 platform. He gave a really nice talk. And I guess you can also directly contact him for a question if he doesn't join us afterwards. So we can directly go to the next speaker, who was Anastasia Varava. She presented a talk entitled State Space Representation for Complex Manipulation, Integrating Geometry, Topology, and Machine Learning. So does anyone in the audience have a question for that talk? Otherwise, I will start with one of the Google Docs. So in the description of the pipeline of the collision space decomposition, at the beginning of the talk, what do the nodes of the connected component represent?
Hi, Naima, thank you. So the nodes of the, sorry, can you please repeat the?
Sure. So in the description of the pipeline of the collision space decomposition, what do the nodes of the connected components represent?
I think the question, okay, I think the person who has these questions meant what are the nodes of the graph that like we end up having?
Yes, I guess so.
Yeah, because, okay, so the, like what, basically we compute the approximation of the free configuration space, of the free space, right, of the object. And then we end up having a graph where basically each connected component is represented as a node. So on that slide with the pipeline, we really mean here connected components that we then can query. So it's really like a simplified representation of the free space.
Okay, thank you. Anyone else in the audience has a question for Anastasia? I can go with the second one from the doc. So in the algorithm presented for caging the formable objects, how does the algorithm know if the object contains a double fork or a neck?
Yes, so we test for both features. So essentially we have a mesh representation of an object, and then we run the feature detection algorithms on the mesh. And then if we find a good neck or if we find a good double fork, then we just use it.
Okay, and what happens is if you find both of them or if you find several forks?
Then we can take the best one, basically like the best one is the one that gives us bigger, like more wiggle room, more freedom in terms of where we can put the manipulator.
Okay, thank you. Thank you for the answer. I have a third question here if no one else wants to ask, so I will go ahead. So in the visual foresight module, how accurate is to consider a Gaussian prior on the variational autoencoder for the set of start and goal states of the short to be folded?
So this is not ideal. We basically, like, this was the first paper that we did in this direction, and it was just kind of a standard choice to set a Gaussian prior because that's how variational autoencoders normally work. But in principle, it's not exactly accurate because it doesn't represent the like the internal structure of the of the state space that we want to capture. So it can be that the state space is disconnected, for example, and then with just a single Gaussian prior, all the states are kind of like, it smooths it a little bit. So like we end up having the illusion basically that the states are close to each other, while in reality they're not. So this is definitely something we're interested in addressing, and we're actually looking into it already now. So if anyone would like to discuss basically the structure preserving autoencoders and structure preserving representation learning, basically ways to preserve the structure of the manifold, I would be really happy to talk about that.
Thank you very much. So yeah, if anyone wants to talk that, feel free to contact Anastasia. Thank you for your answers. I think we don't have any more questions. So if there is no more questions, we're going to go to the next speaker. So thank you for your talk and thank you for the answers to the questions. So our next speaker was Mustafa Mukadam, and he presented a talk on structures policies for active motion generation. So Mustafa, are you here? Yes. Hi.
Yes. Hi.
Okay, so if anyone has a question, I'm going to start with the one of the Google form, and feel free to ask, to write it, in to unmute and to ask it after. So the first question that we got was, will the RMP fusion allow the inclusion of some kinds of task prioritization related to the policies?
Sorry, can you repeat?
Yeah, sure.
Task what?
Task prioritization.
Oh, prioritizations. We didn't explore it directly, but I think it's possible to do that.
Okay. Do you have I don't know, a direction how to do it, or where it could be included?
I mean, if you have heuristics, you can design it. So basically, the Riemannian metrics in these policies have dual functions. They're not only designing the behavior for that specific policy in that task space, but also serve as the priority itself. And so it can be a bit tricky to design them to do both functions. But if you can get it right by hand designing, it should work for your task, or you can try to learn them based on data, which is what the fusion work was trying to do.
Okay, thank you for your answer. I think related to that, we had a second question. So in the RMP flow, how is the tree obtained, and also how are the Riemannian metrics obtained?
That's a good question. A lot of intuition and possibly some learning. So for the tree specifically, I think it's a lot more intuition than learning, although you could try to learn to discover the structure maybe through data, but we haven't really tried that. The tree really comes from the base structure of the robot's kinematics itself. So you already know what the tree for that is going to look like. And then the tree extends out into other sort of abstract task spaces, like distance from the end effector to some goal and things like that. So these spaces are usually very intuitive and pretty much depend on the overall task the robot is trying to do. And so the structure just kind of naturally emerges from that. And of course, if there's something much more abstract that the robot is trying to do and it's not very intuitive to design, maybe it's possible to discover it through just data-driven approaches. And it goes the same for metrics as well. So there are a few follow-up papers from other folks who have been continuing to work on this that try to learn Riemannian metrics from data as well.
Okay, thank you. And to design them, I mean, can of anyone design them just by looking at the problem, or do you have some tricks that you use there? You have some special knowledge on how they should look like?
So besides some properties that you want to ensure, things like these metrics are positive definite. Besides that, there's really just kind of depends on the task itself. And for at least for most of the common ones that you would have for robots trying to move around in environments, doing certain things like reaching a goal, avoiding obstacles, avoiding joint limits, we already specified those along with the paper. So I think unless you're doing something very unique, you probably already can refer to the paper and use those. And of course, beyond that, I think it's kind of hard to design those by hand, which is why learning becomes so much more useful.
Okay, thank you very much. Does anyone in the audience wants to ask a question?
I have a question, Mustafa.
Hmm?
Hello. So probably it's a follow-up on what you were saying regarding the tree. So I'd imagine that, I don't know, possibly a way to automate this tree design is maybe to having a look at the URDF of the robot in order to have like a certain tree structure.
That's exactly
right?
what we did, yeah.
And just imagine the case for a humanoid robot where you just have probably a kind of big tree as a starting structure. And then maybe you want to define different tasks, then you add more nodes in the tree. But then I was wondering if there is a way to somehow, I mean, for some tasks, maybe when it comes to humanoids that have a complex kinematic structure, you might realize in a data-driven way that some parts of the tree are actually not relevant for the task that the robot is doing. I'm not sure if this is already taken into account in the structure or something that you might consider as an extension.
Yeah, that's an interesting question. I don't think we've given it really much thought, but just off the top of my head, I think, you know, the tree decomposition really plays a role if you have task policies living in certain locations on the tree itself. So if you realize that one of those branches is leading to a leaf that doesn't really have a relevant task space where a policy needs to be specified, then you probably don't need that branch. So you can cut off those things just based on the problem you're designing or trying to tackle. Yeah, it would be interesting to see if there's a automatic way to do it. Yeah.
Okay. Thank you, Mustafa.
Thanks. So if there's no more question, thank you, Mustafa, again for your talk and for the answers. And we can go
Thank
to
you for
our
organizing and the invitation.
Thanks. So our last speaker was Luigi Malago with a talk entitled Lagrangian and Hamiltonian Mechanics for Probabilities on the Statistical Manifold.
Hi.
Hi, so thanks for your talk.
Thank you for inviting me for the workshop.
Thanks. So does anyone in the audience have some questions? Otherwise, I will maybe start with one of the Google Docs. So the first one is, could you precise the relationship between geodesic motions, the Lagrangian and the KL Lagrangians?
So can you repeat the question, sorry?
Yeah, sure. Could you precise the relationship between geodesic motions, the Lagrangian and the KL Lagrangian?
So with the geodesics, so I do not fully understand the question, but the point is that so our settings, we are studying a specific type of manifolds, which are manifold of statistical distribution. So if you have a motion and you want to identify a motion, our motion depends on the Lagrangian and depends on the action integral that we have defined. So the three quantities, so we have geodetics by themselves inside this manifold, which depends on the geometry that we consider. In our paper, we consider the Fisher-Rao geometry. The relation depends, I think, on what type of potential you have defined over the manifold and on the specific settings that leads you to the definition of the Lagrangian. I'm not sure if this answered the question, but this is what I understood from the question.
I guess so. Thank you for your answer. Does anyone have a question about this talk? So yeah, maybe a second one that I have here is, could you precise on the similarities and differences between Hessians and statistical manifolds, and either a connection with Riemannian manifolds and Lie groups?
Okay, so statistical manifold are a special type of manifold which have, let's say, more structure than a Riemannian manifold. So this is something more in general of Hessian manifold, in the sense that we can define, basically we have a specific parameterization for which there exists a geometry which is flat, and then we have a dual parameterization which is also flat. And this is a characteristic of all Hessian manifold, which are manifold for which there exists a convex there is a convex potential function which is used basically for the parameterization and for the Legendre duality. So Hessian manifold have more structure than Riemannian manifold, And statistical manifold are a type of Hessian manifold in which the elements of the manifold are probability distribution, for which you have the possibility to define and to link two languages, which is the language of geometry and the language of statistics. And so you have the possibility to find correspondence between quantities, and you have the possibility basically to see the same to see the same quantities from two perspectives. And this is something which is peculiar of information geometry and of the geometry of statistical manifold.
Okay, thanks. That makes it clear. So maybe following this, could you elaborate a bit on the real world application that have those statistical manifolds?
So statistical manifold appears in many different types of applications. So every time you have a function defined over probability distribution, you have a loss function, you have some estimation property based on likelihood, then you are doing an optimization over a statistical manifold. So a statistical manifold is basically a statistical model, which is then described with the terms from Riemannian and affine geometry. So the number of applications is very large. In the talk, we focused on a framework which allows to define accelerated natural gradient, which is a gradient which depends on the specific choice of the metric. So differently from other type of manifold that have been discussed during the previous talk and the presentation, our manifold are special in the sense that they consist of probability distribution. However, the probability distribution could be of any type of object. So we could have a probability distribution over, for example, a different type of Riemannian manifold. So in that case, depending on the choice of the metric, you can include or you can not include the information about the original Riemannian space, your state space, inside the geometry of the statistical model. So this is a choice which depends on the metric. Probably the most famous metric which is able to capture information about the state space is the Wasserstein metric, which we didn't study specifically in this work up to this moment, but it is a way basically to connect the manifold of the state space with the manifold of the statistical models used, for example, to define probability distribution over your action, or probability distribution over rotation, or probability distribution over different type of objects which do not have a standard Euclidean geometry.
Okay, thank you. So there are basically plenty of applications there.
Yes.
Maybe related to just what you said, you were talking about the Wasserstein distance.
Mm-hmm.
So is there any link that you can make between those statistical manifold and the optimal transport framework?
The choice, so the Wasserstein distance is a way to compute the distance between probability distribution. So there are certain cases in which there is a corresponding Riemannian structure associated to the Wasserstein distance, for example, in the case of the Gaussian distribution. In general, you do not have this correspondence, so you're not able to find a Riemannian manifold. However, the choice of the metric could be, for example, the Wasserstein one, or the Fischer-Rao, or other type of metrics that you can define over your statistical model. Is a choice which depends on the application. They have different properties. Somehow this is the same type of reasoning, whether should I use a Euclidean metric of the space of probability distribution versus the Fischer-Rao. It depends on the application. There are certain metrics which have some invariance properties which are useful in application. For example, they do not depend on the choice of the parametrization, but in general, the metric is task dependent, or not specifically task, in the sense that the type of task that you want to solve. For example, if you wanted to consider in the geometry of your statistical model information about how distant are 2 points in your state space, then this is something that you can obtain with the Wasserstein distance, which you cannot obtain with the Fischer-Rao, because the Fischer-Rao is invariant to this type of information. So it depends on what you want to do, and there are applications which use one type of geometry or another. This is somehow the same type of choice that you have when you reason with covariance matrices. So you can define different type of metrics on covariance matrices. Covariance matrix is the space of covariance matrix is a statistical model. And so this is a typical example in which there is not a unique metric which is always the best one, but it depends on what you want to do.
Okay, thank you very much. Thank you for that transparency. It's really explicative, so thanks. Does anyone else in the audience have a question before we finished with the Q&A session? Okay, in that case, thank you, Luigi, very
Thank you very
much for your talk and for your answers. And I will head over to Leonel for the next poster session.
Thank you so much, Noemi. Okay, so we're going to start with the second poster session of our papers. So this session is actually mainly about planning algorithms and also some about representation. We have 6 papers and we're going to proceed in a pretty similar way as before. So we're going to present those that are heavily related to planning problems. Then we're going to stop, do a short Q&A, and after that, we're going to watch the last 2 spotlights and again do a very short Q&A. So let's go ahead.
Hello everyone, my name is Xu Xiao, postdoc at UT Austin, and today I'm going to present our work, Motion Planners Learn from Geometric Hallucination. Motion planning is a classical robotics problem and has been addressed by the robotics community for decades. But recently, many learning-based planners have been proposed using either imitation learning or reinforcement learning. In imitation learning, the planner is learned from labels provided by classical motion planners or from human demonstrations. In reinforcement learning, learning is happening through trial and error. However, both of these approaches require either very high-quality demonstration data or require a vast amount of trial and error data. Motion planning happens in the configuration space C, which is composed of obstacle space and free space. The robot moves from the current configuration CC to a goal configuration CG, using its own action U. We term a sequence of actions a motion plan P. The motion planner is a function F that produces this motion plan P, moving the robot from CC to CG without intersecting C obstacle. It is relatively difficult to find a good function F that maps from C obstacle to an optimal motion plan P. However, if we are given an optimal motion plan P, it is relatively easy to come up with C obstacle in which this motion plan P is optimal. So in this work, we investigate the dual problem of motion planning we call hallucination, which is to find the inverse function of F that maps from optimal motion plan P to C obstacle. However, this inverse function does not always exist because many different C obstacles can map to the same optimal motion plan P. Therefore, given a motion plan P, there could be different C obstacles in which this motion plan P is always optimal. The first approach to address this problem is to hallucinate only the most constrained C obstacle. We call it C obstacle star. Although there may exist many C obstacles where P is optimal, there only exists one C obstacle star in which P is the only feasible and therefore optimal motion plan. So we use this function G to come up with a lot of C obstacle star for many different optimal motion plan Ps. And then we train a function approximator to map back from C obstacle star to motion plan P. For deployment, we want to compute P based on C obstacle star. To construct C obstacle star during runtime, we seek help from a coarse global path from a very fast global planner such as A-star or Dijkstra's, and then we query Q theta minus 1 to compute P. However, G theta minus 1 has only seen the most constrained C obstacle during training and therefore is very conservative. So we need some extra components to adapt P to face the real obstacle space the robot has actually seen. The second approach to address the non-existing F-1 problem is to hallucinate a minimum unreachable set. As shown in the point match example, the robot wants to move from CC via an intermediate point CM to CG. All the black lines in the figures represent a minimum unreachable set. That is, the smallest set of obstacles required to make motion plan P optimal. Dropping any of the obstacles in the black lines will make motion plan P no longer optimal. Therefore, we use one particular C obstacle min bar, as shown in figure D, to represent all C obstacle min. This function O maps from an optimal motion plan P to C obstacle min, and in particular, we use C obstacle min bar to represent all C obstacle min. We also adapt the point match example to a realistic robot with a certain footprint and is also non-holonomic. So as shown in the figure in this slide, so we represent C obstacle using the minimum and the maximum range readings of discrete laser beams. So the orange beams is the reading corresponding to the minimum value of that particular beam, decided by the boundary of the path executed by optimal plan P. and the yellow beam is the maximum value. Some of them are decided by the physical limit of the sensor, some of them are decided by the intersection point of this beam with the obstacle mean bar. And then we can sample between the min and the max to come up with many C obstacles where P is optimal. One example is shown as the blue crosses in this graph. This video shows the hallucinated learning for both approaches. The orange beams represent the C obstacle star in the first approach as the most constrained unreachable set, and we sample between orange and yellow to come up with many C obstacles in addition to the C obstacle min in the second approach. We implemented the motion planners learned from hallucination as a local planner for Jackal robot and tested in simulated and physical experiments. Details can be found in our papers and in our videos.
Hello, my name is Moonyang Lee, and I'll be presenting our early works on geometric footstep planning for dynamic locomotion over uneven terrain. Bipedal robots have the advantage of traversing across various terrains, but poses a challenge of carefully integrating perception and control in order to not fall over. As a result, many implementations of the perception control pipeline are static, meaning that the robot is standing still while it's scanning and planning before taking a step, and inherently treat them as a separate problem. This approach is slow, so we draw motivation from dynamic sensing and motion capabilities of human, as seen in this video. Our goal is to develop a continuous and faster pipeline for our robot. To address this problem, we focus on simplifying our planner to generate an array of feasible footsteps within 5 milliseconds, or under one control loop cycle, and a dynamic controller that can update new trajectories to stabilize its walking pattern. In this talk, I'll focus on the footstep planner. We define feasible footsteps in two folds. First, it has to be collision-free from geometric representations of steppable objects created by our mapping algorithm using a depth camera. Second, it has to be within kinematically reachable workspace, which we further reduce to optimal reachable region for the controller. Solving analytically for this geometric and kinematically feasible footstep is not trivial and computationally demanding, which slows the overall pipeline, and is therefore not really suitable for our dynamic walking scenario. Instead, we resort to a simple but efficient sampling-based planner. We sample a random node within a reachable region, and then perform an overlap test between the two to determine whether if it's a feasible footstep or not. We repeat this process of random sampling of left-right footstep sequence within a fixed number of trials to generate multiple path candidates consisting of feasible steps. When there are multiple feasible paths to take, we choose the best path candidate based on our proposed safety scoring method using a geometric information of the foot and steppable region. Safety scoring is important because uncertainty in the generated map could lead to inaccurate stepping and therefore falling over of the robot. We implement this safety score by generating test points around each footstep and weighting them according to the distance from the edges of the steppable object. For example, when you compare these two feasible footsteps, the one on the left is further from the edge and therefore would have a higher safety score. The overall perception control pipeline of our implementation can be summarized in this video. We use a Kinect camera to get 30-point clouds, which we then segment planes for steppable region. We then represent this region as Octomap for our footstep planner, which generates next array of feasible steps within 5 milliseconds. This fast planning allows for replanning every step for dynamic walking motions. This overall framework can be applied to various terrains to enable bipedal walking without falling over, as seen in this previous and also this scenario. To summarize, we developed a fast perception to control pipeline that allows continuous walking at 0.3 meters per second over various terrains. This is achieved through our efficient sampling-based footstep planner that can generate footsteps within 5 milliseconds. We believe this framework will extend nicely to the challenging terrains for our future work. Thank you for listening to our presentation.
Greetings everyone, my name is Raghav Sood. I am a research associate at Search-Based Planning Laboratory in Carnegie Mellon. Today I'm here to present my research on topology guided path planning for a snake robot in cluttered environments. This work was co-authored by my colleague Mohammad Suhail Salim under the supervision of our advisor Dr. Maxim Likashev. Let's start with motivation behind this research. In this research, we are trying to solve motion planning problem for a tethered snake robot. As you can see in this picture, a robot resembles a snake. It has multiple units connected by revolute joints. The base of the robot is fixed through a prismatic joint with extension limits that limits the reachability of the robot. Navigation environment is a cluttered gas turbine environment with very narrow passages. The goal of the motion planning problem is to reach an end effector pose in robot workspace. Let's consider a small example. Suppose this blue cylinder represents the start pose of the snake robot and the green circle represents the goal that we are trying to reach. If we use something like a traditional 3D BFS heuristic, it will try to guide us along this path. But due to the reachability constraints of the robot, we can get stuck in a minima while using this heuristic. So the method we propose is that we want to explore all the homotopy classes in the robot workspace so that if our search gets stuck along one homotopy class, we can still progress our search along other classes and might find a solution. Now let's go over the overall algorithm. The key idea in our research is that we want to use topology-based heuristics that guide the search along multiple homotopy classes. With these heuristics, we can use a multi-heuristic A-star search that can simultaneously explore all of the homotopy classes during the search. Not all of the homotopy classes induced by all obstacles in the environment are important for a given problem. Therefore, first step in the algorithm is to identify obstacles that induce relevant homotopy classes for a particular problem. We notice that the search majorly progresses along the line joining the goal and start pose of the snake robot in the robot workspace. Therefore, the relevant homotopy classes correspond to motion about these obstacles. We join the goal and the start pose of the snake robot by a straight line. From this line, we calculate distances of all the obstacles in the environment. We then choose the top n obstacles as relevant topology obstacles for calculating the homotopy heuristics. The next step after identifying relevant obstacles is computing topology heuristics for homotopy classes induced by these obstacles. For this, we run a backward Dijkstra search from the goal. We use beam graphs to generate a homotopy augmented graph. More detail about beam graphs can be found in the link provided. We then use this graph to query the heuristic during the search. Let us see an example about how we use homotopy heuristics during search. Suppose our environment has three obstacles A, B, and C. The current robot state in search is crossing beam A, therefore it has a signature of A. From this pose, we can guide the search along three distinct homotopy classes to reach the goal. For this, we query the homotopy augmented graph with three distinct edge signatures corresponding to these three classes. Now let's see how our algorithm performs compared to the baseline. We compare our homotopy heuristics-based algorithm with the standard BFS-based search algorithm. We evaluated the performance over 30 queries with a 1,000-second timeout. You can see that in the plots here, the success rate of our algorithm is about 85%, whereas BFS performs poorly with a 35% success rate. With regards to the planning time, the average planning time with BFS is somewhere around 180 seconds, whereas the homotopy-based algorithms almost just take 50 seconds overall. Here are two examples of paths found by our algorithm in navigating a cluttered turbine. That's all from my side. Thank you.
Okay, thank you so much for such a nice talk. So I would like to know if there's somebody in the audience that would like to ask some questions to the speakers. Otherwise, I can start also with some of the questions that are right now in the chat.
I would like to ask a question to Munyang. Basically, I'm interested whether in your footstep planning, or that is within your safety score, you take into account the dynamics of the robot itself. Like, do you take into account the center of mass, or just because it definitely has a role in preserving stability? Thank you.
Hi, so for our safety score, we actually do not consider the center of mass. So I think that would, so our approach was just to simplify the collision check with the footstep, with the geometric representation reason, which we thought would be much more simple than actually calculating the entire CRM trajectory and checking for collision there. So given our, I guess, our desires for more dynamic and fast continuous walking, we decided to simplify just for 2D footstep collision checks.
Thank you.
Okay, I guess that we have a kind of follow-up question along the same line in the chat, which is made by Mark. So the safety score seems to have a strong influence on your approach. Do you try other heuristics to formulate your safety score?
Not really too sure about the other heuristic methods for the safety score. But we actually, this was kind of like our, I guess, simple and easiest approach that we first implemented and tested right off the bat. And the way, I guess, to kind of talk a little bit more in detail was we just quickly sample, I think we first sampled 8 points and then like 15 points, all within near the generated nodes. And then we saw that the more nodes, of course, we have the more computationally heavy it would require. So we figured it was kind of like an overkill to kind of generate more, because we saw there's some sort of cutoff after 9 points of checking. So we're like, okay, this gave us pretty similar results and without being more computationally heavy. So that was just kind of our, I guess, heuristic method.
Okay, okay, thank you so much. Anybody else from the audience with some questions?
Maybe I can ask one. So for the last talk, so if I understood well, there are topological classes that are defined based on the beams. So one of the questions, how do you define them? And secondly, like how do you define the direction of the beams that are coming out of those obstacles?
So are you asking for the first one or the third talk?
Sorry, for the last one. So for the one with the snake robot.
Actually, I'm not sure we have one of the co-authors of the paper online.
Yeah, it doesn't seem so.
Okay.
No.
Okay, I think we can move on to the second part of the poster session.
Hi, my name is Brian Jackson, and today I'll be talking about planning with attitude. So many of the robotic platforms that we are familiar with move and operate freely in three-dimensional space. This includes things like quadrotors, airplanes, underwater robots, and space systems. So one of the most significant challenges in generating optimal motion planning strategies for these systems is correctly handling the group structure of 3D rotations. So I don't believe I need to provide much motivation as to why unit quaternions are an excellent choice for representing 3D rotations, but I do want to drive home the point that quaternions are linear operators. So as it turns out, pretty much all of the most common operations we perform on unit quaternions can be written as simple linear algebraic expressions, meaning they boil down to simple matrix vector multiplication. So this fact sets us up really nicely for the real motivation of this talk, which is doing calculus on the space of quaternions. Leveraging the linear algebraic versions of the quaternion operations actually makes this much simpler than we'd expect. But first off, why do we care in the first place about doing calculus on the space of quaternions? So across the field of robotics and in optimization-based approaches in particular, we almost always end up taking first or second order Taylor series expansions. So our question is this: how do we efficiently and accurately compute a Jacobian or Hessian of a function like this that accepts and or returns a quaternion? So the key behind doing quaternion calculus is that the space of differential rotations is distinct from the space of unit quaternions. So we can understand this intuitively by understanding that differential rotations live in the plane tangent to the unit sphere of quaternions, as demonstrated in the figure. So there therefore exists a nonlinear mapping between the space of differential rotations and the actual unit quaternion. So when considering the effect a differential rotation applied to the input of a function has on the output, we therefore must take into account the composition rule for the group shown in red and this nonlinear mapping shown in yellow. When taking a Taylor series expansion, all we then need to do is apply the chain rule. We first take the derivative of the function with respect to q, treating q as a vector, and then use the linear algebraic equivalent of quaternion composition followed by the Jacobian of the differential map, evaluated as the differential rotation goes to 0. So we call this last term in yellow the attitude Jacobian, which ends up being the same for any of the maps that we use, such as the exponential or Cayley map. This ends up being a very powerful conversion factor between Jacobians and Euclidean space and the space of differential rotations, as demonstrated here by these very simple expressions for gradients, Hessians, and Jacobians. So to illustrate how this works in practice, we'll demonstrate this on a simple application of Newton's method on the space of quaternions. So let's consider a simple nonlinear least squares problem, which could be representing for example, something like an attitude estimation problem. To apply Newton's method, we first take the Jacobian of the residual function like we would normally, treating the quaternion input as a standard Euclidean vector. This ends up being very practical since this allows us to use any of the tools that we know and love for taking derivatives, such as finite differencing, automatic differentiation, or perhaps an analytic expression where we don't have to worry about the group structure of rotations. We then simply multiply that Jacobian by our attitude Jacobian as shown here, and compute our step in the space of differential rotations, and then use our nonlinear mapping and composition rule to add that step to our current estimate. So not only is this method very straightforward to implement, as we saw on the previous slide, it works just as expected. We recover the full quadratic convergence we'd expect from an unconstrained Newton's method, while a naive method that projects back on the space of unit quaternions after every iteration stalls after just a couple iterations. So we didn't stop there. We're now leveraging these methods in our nonlinear trajectory optimization solver called Altro. So by correctly accounting for the group structure of rotations in the guts of the solver, we got some pretty decent improvements in the runtime and convergence of the algorithm, even despite the extra matrix multiplications. So here's a fun example we included in our abstract. So without the modifications, we couldn't get a quad rotor to do a full 360-degree flip. Instead, it did this annoying unwinding behavior that's all too common when dealing with rotations. So instead, by adapting the algorithm to correctly take the derivatives with respect to the group structure of rotations, the solver converged easily and fairly quickly to a pretty nice trajectory. So in conclusion, we've presented a straightforward method for adapting existing gradient and Newton-based algorithms to correctly account for the space of rotations. In contrast to many other approaches, ours is built entirely on linear algebra and vector calculus, both of which should be very familiar to pretty much everyone in robotics. With that, thank you, and I'm happy to take any questions.
Hi, this is a poster video for our workshop submission configuration space approximations in high dimensions. Configuration spaces are one of the central concepts in formalizing various problems in robotic manipulation and path planning, which includes topics such as connectivity analysis as well as the problem of cage verification, which checks if an object cannot escape arbitrarily far from its initial configuration within its free space. When one tries to reconstruct or approximate a configuration space, it quickly becomes infeasible when the dimensionality of the space grows. Even in a three-dimensional case of a moving object, when the configuration space becomes six-dimensional, configuration space construction becomes very computationally heavy. In our previous work, we proposed a decomposition-based method to build approximations of three-dimensional slices of the free space using spherical-based representations of objects. In order to work with representations such as the union of spheres, weighted Voronoi diagrams come into big use. A Voronoi diagram for a given set of points, represented in blue here, is a space partitioning into cells where each cell contains all the points of the space closest to a corresponding data point. Dual to these diagrams are Delaunay triangulations, shown in orange. In addition to previously discussed caging task, this construction can also be used, for example, for optimal path planning or path existence verification. However, as discussed earlier, the usage of these diagrams is usually limited to low dimensionality due to exponentially increasing geometric complexity of the diagrams, which normally prevents their explicit construction in dimensions above 5 or 6 for a reasonable amount of data points. Recently, we proposed a methodology that alleviates the high computational cost of the diagrams in high dimensions. In particular, we propose a way to explore the structure of Voronoi diagrams without their explicit construction. This is done by performing graph traversal algorithms in a possibly extremely large Voronoi graph, while simultaneously extracting necessary information about Delaunay triangulation. One of the proposed methods includes random walk, which iteratively reconstructs an increasing subset of a Delaunay graph, which quickly converges to a real Delaunay graph. The complexity of the Delaunay graph is significantly smaller than a Voronoi graph. Here we can see a small 3D visualization of this approach with the Voronoi diagram on the left and the Delaunay graph on the right. After finding an initial set of vertices on the left, a random exploration is performed. Each visit to a vertex on the left is equivalent to visiting a tetrahedron on the right, which contains several edges of the Delaunay graph. It is important to note that one of the proposed raycasting complexities is logarithmic when the amount of points is significantly larger than the dimensionality, which is the case for many robotics applications. The second graph algorithm which we consider is a directed graph walk called the visibility walk. It is equivalent of walking along the high-dimensional tetrahedra of the Delaunay triangulation towards some query point, and can be used to find the simplex that contains the point. The algorithm is deterministic and does not require any explicit construction of the triangulation. To reiterate the main idea, the discussed methods allow us to use Delaunay triangulations in domains where the full explicit construction is infeasible. We see this methodology as highly applicable in robotics data due to its interest in topological structure and medium dimensionality. We consider an approach of representing a collision space as a set of randomly sampled collision neighborhoods, in which case the free space can be computed as the complement of the simplicial complex representing the set of collisions. While constructing a full simplicial complex might be practical, we plan to approximate it with a Delaunay graph, otherwise called natural neighbor graph, obtained from a random walk exploration. From a given configuration, we can perform a visibility walk to determine a simplex of the triangulation that contains it, and based on that and the connectivity analysis of the graph, we may infer whether the configuration is caged or connected to other configurations. Thank you for your attention.
In this paper, we present a novel approach to the long-standing problem of multi-view point cloud synchronization. To formulate the problem, we are given a number of 2D scans of some underlying 3D object, and we are then asked to reconstruct the underlying 3D object from those 2D scans. The traditional approach to solve this problem is split into two stages. The first stage is to estimate the relative poses of the cameras with each other. And the second stage is to then solve for some global alignment of all of these 2D scans in some global frame, essentially gluing them all together into the 3D object. Our approach is to then completely circumvent this erroneous and expensive first stage and just solve for some global shape that agrees geometrically with all of the data given by the partial views. The way we solve this problem then is to embed our data into a transformation invariant space, which we use the Euclidean distance matrices for this. So for our problem, we first represent all the point clouds from the views by their distance matrices as depicted by the blue squares. We then create a global distance matrix that matches for some synchronization with all of the viewed distance matrices. And finally, from that distance matrix, we can recover the bunny. While optimizing over Euclidean distance matrices would already be nice, we can instead optimize over positive semi-definite matrices, which would be even nicer. So to see this, if we consider the point cloud as in this matrix form, where you stack up the columns as the points, and then consider the gram matrix G of this point cloud, you can write a formula for the square Euclidean distance matrix in a very nice way with respect to the gram matrix. What this then yields is a unified optimization problem for our goal. So what we are doing here is finding some point cloud Y, such as its distance matrix D of Y matches all of the data distance matrices D sub I for some permutation P sub I. The SI matrices are just downsampling factors to make sure that the size of this bigger distance matrix matches that of the smaller distance matrix. And finally, since it's very hard to optimize over permutations, we relax this set to the tightest convex relaxation, which is the Birkhoff polytope, or otherwise known as a set of doubly stochastic matrices. Here, our optimization space is an outer product of Birkhoff polytopes and the set of positive semi-definite matrices. These are both sets that are well understood geometrically and have submanifold structure that is well understood and has all the geometric tools that we need to develop Riemannian versions of your favorite first or second order optimization algorithms. From here, we also want to consider a regularization term to better promote good global minima for this full optimization, since we expect it to be hard. What we consider for our paper is a sort of relaxed constraint of the downsampled versions of our point cloud Y, Pi, Si being some Euclidean transformation of all of the views Yi. So this is a matrix version of it where Ci, these are the centering operations. So what it's saying, and A is some matrix in the special orthogonal group of 3x3 matrices. So what this is saying is that when you center both of the point clouds, there's going to be some rotation that matches them. We can relax this constraint to say just some matrix A rather than it being SO3 exists. And if we have this constraint hold, we can represent a regularization term we expect to be 0 for solutions in a very nice way. So the QIs here are QR factorizations of the observed point clouds Yi, and the Ci matrices are as defined before. This is the centering operation. From here, we can get results. So for this extended abstract, we tested on a simpler version of the problem, which is just synchronizing two different views of the same object. So we're just optimizing over a Birkhoff matrix P with a regularization term as defined before. The main results for this paper are the fact that as you rotate the two views away from each other, for the radians of rotation here, you see that obviously our method does not change in performance, but if you use something like ICP, this will deteriorate rather quickly. And even if you add Gaussian random noise to the points of one of the views, our method stays relatively redundant to that noise in finding a good synchronization. From here, we hope to develop these methods into an end-to-end algorithm that will take any number of unsynchronized views and be able to recreate the underlying 3D object. From there, we can consider an even more general version of the problem where, for example, instead of Euclidean distance matrices as our data, we consider general Riemannian metrics. You can see how synchronization performs there. Thank you.
So this was our last poster. So do we have any question on those talks from the audience? You can write it on the chat or ask. Yeah, Philip, I still have the microphone.
Yeah, I have a question for Michael. So I'm interested, you mentioned that, so
given that you may have multiple point clouds that are different, that show different parts of the object, how do you construct this big distance matrix from these smaller distance matrices? How do you know how do you know like the ordering of these distances? How do you know how to construct it? I hope this is a clear question. I'm not super familiar with this problem.
Yeah, no. It's a good question. And this is probably the hardest part of this optimization. And the big part is making sure that the permutations, the P of I, are well constructed. So let's say you have like a 600 point cloud, this like the full bunny, and each of the views, let's say, is about 300 points. So these synchronization matrices, the P of I's, are going to be 600 by 600. And the SI are sort of downsampling to make sure you know that the points of the full point cloud are sort of correctly correspondent to whichever view you're going off of. Now, as you may be aware from optimizing over EDM, sometimes this problem can not do too well. So if you have a bad initialization, this can lead to bad optimization. So an important part of our end-to-end method is making sure that these synchronizations are optimized at least somewhat well. You don't need to get them fully correct, but if you at least give some of an idea, we didn't show results in this abstract, but so far from our tests, we're showing that you can get sort of an idea of the shape, even if your PI matrices are fairly erroneous. And from there, it's just sort of, we're doing a coordinate descent optimization where you're sort of optimizing the same loss over the Berghoff matrices, the PI, and then the point cloud for the full distance matrix. And so far the results are good, but obviously we have to wait and see. But thank you for your question. Hopefully that answers it.
Yeah, that's a great answer. Thank you.
Thanks. Do we have any other question?
I do have a question for Brian Jackson. So I'm just curious about if he explored already off-the-shelf Riemannian optimization techniques for the problem that he faced and why he decided to adapt Newton methods or gradient-based methods in such a way.
Yeah, that's a great question. So we haven't done too much like comparison with other, I guess, Riemannian solvers for optimization. We're kind of approaching this very much from the control side, and there's a lot of kind of inherent structure to the control and MPC problems that we're looking at that we wanted to adapt the kind of existing like highly tuned and highly efficient solvers in that community to operate efficiently on the space of rotations. And currently in the control community, at least that we're familiar with, we haven't seen a whole lot or really any availability of solvers that kind of to tackle both of these problems at the same time. So tackling the kind of the underlying structure of the rotation, underlying structure of rotations, and the kind of the MPC or Markovian structure of the problem. So that's kind of the direction that we're coming from. Hopefully that answers the question.
Yeah, sure, cool. Thank you.
Thanks. So do we have any other question? Okay, so thank you again to all our spotlight speakers for their nice talks. And I think we can go on now with the panel discussion. So for that, I'm going to hand over to Leonard for the first question.
Okay, thank you, Noemi, and thank you again to all the authors of the papers who attended to the spotlights presentations and that were willing to answer the questions from the attendees. So yeah, according to the agenda, now it's time for the panel discussion. And for that, I first would like to highlight two really cool things that we have about the workshop. So the first one is that we have a really broad range of speakers. So we, as you saw in the YouTube channel, there are talks about perception, control, planning, and even a really mathematical level, such as the one of Luigi Malago. On the other hand, what we really like as well is that we managed to reach out authors of papers coming from all over the world. So we got submissions from universities or institutes in Asia, America, Europe as well. So I think that's actually a pretty good result, and also that shows us somehow that the topic is quite active all around the world. So to start the panel discussion, I know that some of the speakers couldn't make it because of time zones and other commitments right now that make it difficult to gather other people for this kind of Zoom-like workshops. But first of all, I will try to bring up some questions that we collected from the organizers of the workshops. But we also would like to encourage all the people in the Zoom channel to come up with questions or maybe comments regarding how to bring geometry methods in different kind of robotic applications. So probably one of the first questions that comes to my mind and that we had prepared actually with the organizers is regarding the computational cost of bringing geometric methods into optimization or learning algorithms. At some point, some people may argue that this is actually a showstopper to use these methods in practice. For example, you want to control a robot in real time. Such kind of optimization methods that are heavily expensive might make geometric aware methods less attractive. And I was wondering if you guys, I think that Bruno has a lot of experience on using dual quaternions in different kind of applications, even in collaborative manipulation. And I would like to ask you, how do you think that we can achieve a good trade-off between the kind of computational cost that these geometric methods might bring, and how we can really try to convince people that it's actually imperative to bring this geometry awareness in their methods?
Yeah, I think it's a great question, and I think that the solution for that problem would be to, exploit the geometrical structure of the problem. So you mentioned two-arm manipulation, and actually, yeah, we do it in real time, so we can generate the control action in less than 1 millisecond, much less than that, using a standard C++ implementation, but for that, we must try to well, I would describe my approach, which I think it's better, it's easier for me to explain. So I use a bottom-up approach where instead of starting with a very broad and general idea and then specializing to a specific geometrical representation, I invert the reasoning in the sense that I start with, modeling and establishing relevant geometrical primitives. And from them, I ensure that I can do everything in a very efficient way. And then from there, I'm going up to the upper levels. So for example, in order to control the robot using two arms, for example. So I have the model, the analytical model, directly in dual quaternion algebra for one arm. Then I can combine them in a very systematic way. So I have two arms now with the corresponding Jacobians. And then we can use useful abstractions. For example, if you want to control, let's say, a firmly grasped object, for example. So instead of focusing on the arms, we can focus on the object, which is the relevant parts to be manipulated. So we can think about, absolute poses and relative poses, where the relative poses is related to the relative pose between the two effectors. So you can use it to bend, stretch, and do whatever you want with the object. And the absolute pose would be the absolute pose with respect to a reference frame in the world. In this way, you have 12-dimensional manifold, and that's it, because you need 6 dimensions for the absolute pose, 6 dimensions for the relative pose. And then you can abstract that such that you can use two manipulators with 100 degrees of freedom each one. It doesn't matter, and that's it. That's the idea. So it's to use suitable abstractions so that you can leverage all the geometrical properties that you have in your problem. And this is the way I've been doing, and I've been able to implement it in everything in real time, even doing constraint controllers, designing constraint controllers where I can take into account, nonlinear constraints that I transform in linear constraints by using differential inequalities. So it's exploiting the problem structure that I think that we can do it in real time.
That's pretty cool, Bruno. Thank you very much, because I guess that actually talking about the experience that you have by implementing all these approaches in different kind of, because I saw in your talk that you really had a lot of experiments out there where you can really showcase the use of the quaternions in kinematics and control. And I think that's actually pretty good to see that you can really run these algorithms in real time. I think that really makes people aware that these approaches can really not only provide a principled way to understand the problem, but also in a practical sense, it's actually something possible to implement. I think that's pretty cool. I was wondering, I'm not expert at all in state estimation, which is the work that Joan and Sola has been working for several years. But I'm curious about, I don't know, what was your take in this computational cost of the approaches that you use in for state estimation? I don't know if John is around. Well, if not, I think that Maxim probably, I think I saw him around. Okay.
Sir Leonon,
yeah, Maxim.
Is that a question to me? Sir, I missed that.
No. Yeah, I was actually sharing a concern or a question that I had regarding the computational cost that some of these geometry-aware approaches might lead to, that may stop people from using them in practical applications. I saw in your talk that, for example, I think that's a really good example when you're actually showing that, for example, using Euclidean-based metrics wouldn't even solve the problem at all. And I think that was actually a strong message in your talk. And I was wondering if actually this could be a key message to encourage people to bring such methods as the ones that you have used that are more principled in a geometric sense for practical applications. And then what is your take about the whole computational cost that these may still show?
Yeah. So I mean, there is some sort of balance I think exists between the amount of computation that you can afford on doing the kind of geometrical reasoning and so on, and the benefits that it provides towards the getting the real-time performance out of the overall system. So in case of what I was talking about, there having some geometrical reasoning and having a computation, solving those low-dimensional problems using some of the geometry into account can give you tremendous speed ups to the point where you're getting a overall real-time performance, as opposed to if you don't do it, then you're going to be dealing with a very high-dimensional planning problem with no kind of guidance. And therefore you will not get the real-time performance. So it gives you this benefit. Now, I think more generally, the question is where you can apply geometrical reasoning, where you cannot. And there are a lot of problems in robotics that are kind of semi-structured. They're not as arbitrary as, like, a robot walking in a household domains. But, if you take problems like in manufacturing, in warehouses and so on, in those settings, the problems are quite structured. Yes, there's a lot of components to it that still can be unpredictable and so on. And you kind of can separate it. There is a lot of structure that you expect, and then there is other things that may happen spontaneously. So as much of the first part that you have there, you can apply a lot of geometrical reasonings over it. You can spend time on the kind of designing the algorithms that exploit that information. And then in real time, you're relying on planning algorithms to be able to deal with the new things that are going to come up while taking advantage of as much of this reasoning that you can as you've done based on that first portion, the things that already exist there. So for semi-structured or structured problems, I think there's a lot of opportunities to apply a lot of geometrical reasoning with the idea of speeding up the overall computation.
Okay, thank you, Maxim. That's a really interesting view.
Sure.
So I guess that now maybe we can check our next question that we have for the panel. Noemi, you want to take over?
Yeah, sure. So the next question I wanted to discuss is which fields of robotics are currently missing to exploit the benefits of geometric methods. So in your opinion, in your work that you see every day, so we have a lot of different speakers with a lot of different topics. So we would like to have your opinion on that. So maybe we can start with Taeyoon. In your talk, you showed how to estimate dynamical parameters by using those geometric methods, while those estimations were done without before. So do you have any opinion on that? Any thought on which fields of robotics related to your work could be still missing those geometrical methods?
Yes, I've also been wondering, like, what are the other fields, where, what kind of, where should we look at, okay, so I will just give one example. I think one kind of structure that we might look more, especially in control and estimation, is about I think stiffness is quite important. One important one. Maybe one can think like stiffness is just for example, for the case of 6-dimensional space, stiffness is a 6 by, not just simply a 6 by 6 positive definite matrix, but they actually have a lot more structure than just a naive 6 by 6 dimension matrix. There's a nice paper by John Loncari about actually actually there's a more structure that we can exploit from the stiffness matrix. So I think stiffness also think that we should look more closely, and also, you know, as I just made out in the slide, in the last part of the slide, I think the robotics is just full of variables with ample structures, just like context or transformations and many things. So I think there's a lot of part missing, especially in the learning side. And yeah, I want to hear about the opinions of other speakers.
Thank you for your answer. Yeah, I mean, this is really interesting. So yeah, maybe we can ask the opinion of other speaker. Maybe if Joan is back, he was talking about that also when we asked him question about his talk before. So maybe Joan, you want to say something there? No, okay. It seems that he's not back yet. So maybe we can also ask Anastasia. I think you were talking also about the structure that you wanted to add in the variational tone coder. So maybe you also have some opinion on which field of robotics are still missing to exploit those geometric methods.
Yeah, I mean, like my general opinion is like, especially if we're talking about it from a learning perspective, like everything that has to do with learning for robotics, I would like to basically see more structure and more prior knowledge incorporated into representation learning, reinforcement learning for robotics in general, because currently what we see is a lot of end-to-end kind of methods that are really data inefficient. And at the same time, we know a lot about the geometric structure of the problems. So like for me personally, it would be very interesting to integrate this geometric knowledge into learning. In my case, mostly learning representations, but I think it's also relevant for things like reinforcement learning.
Anastasia, I have a question about that. So I'm just curious about how much prior information or how much structure you can really exploit when it comes to represent or manipulate the formable objects, such as the case that you presented in your talk.
Right. So this is exactly the question that we're trying to answer in our work. So what we would like to do is basically consider families of tasks. So for example, if you work with clothes-like objects, then you can do different things with them. You can fold them, unfold them, pack them, maybe like even try to do some assistive dressing scenarios and stuff like that. So it's basically for like this kind of tasks, like if you find a good level of generality, for example, that you know that you're going to work with clothes-like objects, then our idea is that you can use some like prior knowledge that is shared between all these types of tasks. But at the same, so it's like it shouldn't be too general, but it shouldn't be too specific. It shouldn't be basically like it's a trade-off.
Okay, thank you. Anyone else wants to add some comments on that? Okay, maybe we can move to the next question. I think that we have a question from Philip that I would just ask to all the panel. So, are you aware of any interesting approaches using geometric methods in other fields, such as computational chemistry or physics?
Yes, if I may. In theoretical physics, they are now using a lot of Clifford algebra, which is very, well, one particular instance of a Clifford algebra is related to dual quaternions via isomorphisms. But they use very general Clifford algebras where you can introduce new imaginary elements which have some special properties, and then you can represent a lot of things. And there is one researcher, his name is David Hestenes, who has been working on Clifford algebra in order to rewrite not only classical physics, but also relativity, general relativity, and for some problems, physicists have said that it's very difficult to use, non-geometrical and classic representations because you don't have enough mathematical tools to express your ideas concisely, which means that in order to have something that is verifiable from a theoretical point of view, in order to present your ideas, in order to prove new theorems, you need a whole new language. So they are using Clifford algebra, which is very related to dual quaternions and also to geometric algebra.
That sounds pretty cool.
Sorry, I just wanted to follow up on the question. Is there maybe a good resource that you're aware of on just on Clifford algebra in general?
Yes, I can. I have some. Well, I have even one of Hessene's book. It's not so easy because he starts from the algebra axioms and then, but in a very abstract way. But nonetheless, I would say that if you have some knowledge of Clifford algebra, you can follow it. So my strategy when I started learning about Clifford algebra, I saw some other introductory resources, and then I continued to study Hassan's book. I will take the exact name here, and I will post on the chat.
Thank you.
Welcome.
Thank you so much. I think there is another question from Juan, who is asking, can geometric methods be applied to unknown object segmentations in RGBD images, for example? So I'm not sure if any of you might have some background on such kind of field. I don't have any background. I am aware that some people have done it because of some colleagues' work on that topic, but I cannot really elaborate on that. So I'm not sure if somebody else would like to comment on that question. Well, it doesn't seem so. Maybe from what I can tell you, Juan, is that so I cannot recall right now the authors of those papers, but there's a set of researchers that have tried to bring some of the techniques that are used to model objects in graphics. I think one of them is his last name is Crane, who is quite famous in the use of Riemann manifolds to represent geometric features in graphics. And I know that some people have extend or use some of his techniques or his approaches for object, for example, object recognition, and maybe for object segmentation. But I cannot recall right now. I might do my job later to share some references, but I'm aware that some people are working on this from that perspective, from the graphics perspective, let's say. So maybe, Noemi, you want to move on to the next question if we don't have any more questions about that?
Sure. So the next question is from your experience on geometric methods in robotics, what are the most complex aspects of exploiting this geometry awareness in your research? So which are the bottleneck that you're encountering when you're doing your research on that topic? What are the aspects that are complex that you need to tackle? Yeah, I don't know if any one of you wants to take the first answer to this question. I think Bruno and Joan were talking also about that before, saying that it was you have to understand the math and then you can move on. I don't know if Joan is back to say something, or if Bruno, you want to say something about that.
Is the question more related to learning the theory behind it in order to apply it, or complex in terms of developing new techniques?
I think you can see it as both. It's kind of related, no? It's like you need to understand the techniques to be able to then develop something new, right? So
yeah, that's true. But I mean, for example, I think that a great challenge now is to couple high-level symbolic reasoning, which involves geometry, with low-level geometric reasoning, which is more numerical. I mean, for example, suppose that you want to define a very high-level task, such as that usually is done by using discrete planners like LTL and other planners, such that you say, take this cup and place it inside the cupboard, for example, and the cupboard's door is closed. The cup is inside a drawer. The drawer is closed, like in the example that I showed in my presentation. So in order to do high-level planning, you have to reason on a discrete space, which usually does not takes into account the continuous aspects of the geometry involved in the problem. So to me, one of the challenges is to translate this high-level information directly into low-level information, so that you don't need to use very intermediate, a lot of intermediate steps, which usually introduce singularities, discontinuities. Sometimes you have to use different planners, which takes time. So in order to do fast planning, but in a high level way, such that robots can really be very useful for humans interacting with non-expert humans, I think that we must bridge this gap. And to me, this is one of the most challenging aspects. And maybe learning can play an important role on that, because some missing pieces can be filled in by using learning, I think.
Yeah, I think this is a nice idea. Definitely learning may be useful in that sense. Thank you for your answer. I think maybe to follow up, Luigi, I think you had the most mathematical presentation that we had. Maybe you want to say a word on that?
Yes, so I think that what is interesting for me is to move next to understand how the technical framework that we have developed together with my colleagues can be developed in application. And so I was very interested in the talks, because I saw plenty of possible application for Riemannian method. And so I think from my perspective, what is the interesting part is to see how we can fill gaps which are computational, as you mentioned previously, but also of the proper setting in order to understand which method is the best for the application. So I agree that my talk was much more, I mean, it was a little bit different from the previous one in terms of the perspective, but I think that the gap between this and the application is one of those gaps that can be filled, and the purpose of the type of research that we do is to try to move from mathematical frameworks to applications.
Thank you. Yeah, I think this is a nice, it's a nice example where mathematicians or people from machine learning can work with robotics to bridge some of those gaps. So maybe we can go to the next question, which is the last one that we had for the panel. So this question is, what are the current or future challenges that you see in your field when it comes to geometry awareness? So maybe we can go back to Taeyoon. Do you have any answer to that? Is there some challenges that you see based on the work that you did on those dynamical parameter identification? What do you see next?
Maybe I want to mention some progress on robot learning side, like as a roboticist, I think like we see maybe this is a bit cliche, but we see a lot of progress in the neighborhood community, like computer visions and natural language processing by the success of deep learning. But I guess the major success was the success would not be possible with just like naive fully connected neural networks, right? Like I think in their domain they are specifically engineering very domain specific model that can be used very effectively, like CNNs or like even transformers or GraphNet models. So I think, but when I see, I'm not judging all the approaches in robot learning, but I think a lot of works, especially in reinforcement learning, is just confined to a very simple neural network structure. I think we should really start to think about what kind of model is the most effective in robotics problem. And I think it's could be much more interesting topic because, like as I said, in robotics, most of the variables that we work with are very are data with a lot of structures. Like even to designing a model that maps something to others. We first is actually we are defining some calculus on the data that lives on manifolds. So even a simple operation should make sense. For example, should be holding invariant or something that should be physically meaningful. So I think building a geometric aware model for robot learning control would be one challenge that I want to highlight.
Thanks. Yeah, I think I agree with that. We're still missing some model and some geometry in both learning and control. So definitely is an interesting direction. Maybe Maxim, do you have something that you would like to share with that? Related to your talk that you were more in the planning side. So maybe from the planning side, what are the current or future challenges that you can see?
Sure, yeah. Let me, I guess, maybe say a few. One is when it comes to kind of running it on a real robot operating in spaces that are either partially known or dynamic. You're getting a lot of input at every single frame from sensing. You're rebuilding the maps, you're rebuilding the knowledge of the environment, and that necessitates, if you are employing any sort of a geometry-based processing, that necessitates the functionality to do it fast in incremental fashion. So you basically, rather than rebuilding the entire whatever the doing geometry reasoning over it, like in my case, the identifying the objects around which we should be considering topological classes, and then rerunning the resolving this low-dimensional manifold. Can we do it incrementally? Can we do it fast and taking into account the fact that we've done a lot of that in the previous step, and the changes tend to be local to the geometry that we've just observed. So like that's one.
Posso chiamare fra un attimo?
I'm sorry?
Tutto bene?
Oh, okay. The other aspect is I'm actually quite interested in the domains where robots can interact with the environment, and let's say manipulation, whereas you're trying to grasp the objects, you either in some sort of deliberative fashion or just in kind of a non-prehensile fashion, you interact with other objects. If you are employing any sort of geometrical reasoning, in particular, like reasoning about different topology classes that you utilize for getting to the objects, that implies that now you're doing planning where the topology classes may change on the fly, the topology classes that exist there. You're moving the objects, the multiple objects can collapse into one single object, closing up the topology classes. So can you have methods that allow you to reason about these different topologies and how they can be modified on the fly? So then I don't have a kind of answer to that. So this is just something that we're starting to look at.
Thanks. Yeah, it sounds really like an interesting direction. Yeah, to take into account all that domain knowledge or those transformation of your states into account in the algorithm. It could be really, an important challenge for what's coming. Thank you.
Sure. Thank you.
Does anyone else of our speaker wants to say something about this last question? Okay, so I guess in that case, we can move on to the last part of this workshop. And we have a question from Philip.
Oh, no, it's not a question.
It's not a question. Sorry. Sorry. Okay, so we can move on to the last part of this workshop, which is the awards. So I will hand on to Leonel for that.
Thank you so much, Noemi. And thank you all the speakers and all the attendees for being just at the very last part of the workshop. So as you may know, the workshop was sponsored by the Bosch Center for AI, and the Bosch Center for AI is actually supporting a lot of programs for researchers out there to, for example, carry out some short internships in our campus. We have different campuses around the world. There is one in the US, well, a couple in the US, one here in Germany, and a couple more in Asia. And as part of the whole research strategy of Bosch, we wanted to also show that we really believe in research, in basic research, and therefore we wanted to sponsor an award for the best contribution for this workshop. So how do we do that? So in the first place, all the papers that were submitted were actually reviewed by at least 2 reviewers. We did consider the scores given by the reviewers, but also the organizing committee had a look at the spotlights that were actually prepared by the authors of these papers. Well, we also had a look in the spotlights, but not only the technical part, which is actually probably more clear in the papers, but also the clarity of the approach, the impact that it may have, and also the full design of the spotlight, like how it was actually a target for the audience. So with all these criteria, we come up with a decision that was not easy to make, but I'm happy to announce the award for the best paper of this workshop. And please, Noemi, you can just disclose the winner. So it's actually the paper of Philip and Matthew. I think that both of them are actually right now still in the workshop. It was a pretty cool job. Actually, we found really good jobs as well from other papers. It wasn't an easy decision, but we believe that in the whole set of criteria that we consider, this is actually the best contribution for this workshop. So congratulations, Philip, Matthew, and colleagues. It's actually a pretty good job. And I will be in contact with you in order to arrange the whole award procedure. So congratulations, Philip and Matthew. I'm not sure if you want to give some words or.
Well, I'd just like to say, yeah, it's we've actually we're just submitting kind of like a full version of this paper to a journal. We've just finished it yesterday, so yeah. If anyone is interested in a while, I'm sure you will see a more detailed treatment. Thanks again for this workshop. I think it was it's a great idea, and there's obviously a lot of interesting applications for distance for just geometric methods in general. And yeah, that's it.
Okay, congratulations, Philip, again. So I think now, Noemi, you can move on and conclude the workshop.
Sure. So congratulations, Philip and Matthew. It was a nice paper and a really nice presentations. So to conclude the workshop, so first, thank you all for attending. You made a great live session. Thanks to the speakers. So first for accepting our invitation, for giving really nice talks, even if it's not that easy to do everything by recording them, but we really got super nice talks. So thank you. Thank you for being here today to answer the questions of the audience. I think it was really great discussions. There is a lot to do there. I would like also to thank all the authors of the abstracts. You submitted your work to our workshop and you contributed in a great way. As Leon said, we had really great abstracts. So thank you for that. just for all of you to know, all the videos of the speaker will be, are already on YouTube, and all the papers that were submitted to the workshop, that were accepted to the workshop, are on our website. So go to the website, check them. There are really nice works there. Then I would like to thank the organizers. So my co-organizer that did a great job organizing this workshop. So thanks Leonel, Soren, Hans-Peter, and Sofrit. I think this workshop was really a great success, and is also thanks to you. And finally, I would like to thank our sponsor, so the Bosch Center for Artificial Intelligence, who provided the award. So thank you, everyone. Check the talks and check the papers on our website for the one that you didn't check yet.
Thank you, everybody. Stay safe, and thank you for attending. Bye-bye.
Thank you for organizing.
Thanks. Bye-bye.
Thanks, guys. Bye.
Thank you. Bye.